Agam sir, are you there?
We still have 7 minutes, I suppose.
Yes, sir. Just 1 minute. I will make you presenter. Actually, my computer becomes very slow. Rajesh, can you make sir presenter? Because okay, yeah, make sir as a presenter.
Is it visible now?
राजेश, yes sir, it's visible.
Good.
इसको सर फुल स्क्रीन करके एक बार चला के देखिएगा, फुल स्क्रीन कर लीजिए, एक बार चेक कर लीजिए।
चलेगा सर, चलेगा। I have checked yesterday.
बस
Yes sir, working well.
Yeah, working well, fine.
Okay, fine sir, fine.
किरण सर उस पे भी आ गया, यूट्यूब पे शुरू हो गया स्ट्रीमिंग।
There sir, Sarabjot, are you there? सर सर्वजोत है क्या वहां पर?
पता नहीं, अब इतने बंदों में देखना क्या दिख रही है।
सर्वज्योत इज हियर
है, वो दिख तो रही है, इधर उधर होगी वो, साथ में 10:30 बजे आ जाएगी सर वो।
राजेश,
यस सर।
can you tell her to call me please?
Hello, Boto.
ओके।
राजेश,
मैं करता हूँ सर।
सर शी इज ट्राइंग टू स्पीक बट हर वॉइस इज नॉट ऑडिबल।
no, tell her to call me actually.
ओके एंड आल्सो संसार कैन यू ट्राई स्पीकिंग?
उसको किरण सर उसको प्रेजेंटर बनाओ एक बार, उसको भी राइट्स दो, फिर वो कर पाएगी।
Rajesh, can you do that? Okay, I
Yes,
will
sir.
try.
सरबजोत कौन से कर रही है?
सर ये नॉन एनआईटी जैसे कर रही है।
तो उससे ना करे।
संसार भी तुम नॉन एनआईटी जे डोमेन से लॉगिन हो इसमें ना।
नहीं, वो कोई प्रॉब्लम नहीं है। एक बार यूजर नेम बताओ मुझे उसका।
यूजर नेम
हमें वो दिख भी नहीं रही।
नहीं सर है अभी।
नहीं, हैंग हो गया, मेरा सिस्टम हैंग हो जा रहा है बार बार।
हाय सर, अब बोलो एक बार देखें।
Sarabjot, are you there?
हाँ सर, हाँ नहीं, वहाँ पे सुनाई नहीं दे रहा है आपको। ये आप फोन है आपके पास? फोन में इंस्टॉल किया है आपने?
संसार भी वहीं बैठा है तो उसके पीसी से ट्राई कर सकती है।
आप सरबजोत फोन से लॉगिन करो, फोन से।
अच्छा सर, देखो अगर सॉल्व होता है, अदरवाइज वी विल स्टार्ट।
हाँ आप शुरू कर दो किरण सर, कोई बात नहीं, उसमें क्या है, आपके पास पड़ा तो है सर का।
कोई बात नहीं सर, किरण सर करते हैं शुरू ना।
शुरू कर दें?
यस सर, लेट अस स्टार्ट।
हाँ, she will be joining afterwards, कोई बात नहीं।
Just 1 minute. Okay sir, so I'm going to start.
या बिल्कुल।
So very warm good morning to all of you, and I welcome you in this second day of this short-term course on advanced energy material, the first session of the day. Today it's a privilege for us that Professor Rajiv Ranjan is with us. So Professor Rajiv Ranjan is from IIC Bangalore. He does not need any introduction. So he is a very famous scientist. So his area of interest is ferroelectric material and piezoelectric material. So Professor Rajiv Ranjan did his PhD from Institute of Technology from Banaras Hindu University, Varanasi in 2000. After that, he worked as a postdoc fellow in Germany. So he is a Harvard fellow, and he has received many awards. For example, I will read a few of them. He is fellow of Indian Academy of Science. He is fellow of Asia Pacific Academy Material. He is the recipient of Materialist Award in year 2018 by Department of Science and Technology, Government of India. And he has published more than 160 research articles in different area of research. So today he is going to talk about the new development of ferroelectric materials and piezoelectric materials. As you all know that piezoelectric materials are very, very useful. You are using piezoelectric material every day in your kitchen. So today you will have more excited applications of piezoelectric materials. So without any further delay, I request Professor Rajiv Ranjan to please start his talk. Thank you, sir. Thank you very much. for accepting our request to be a part of this course.
Thank you, Dr. Kiran, for the introduction. So I can start now, right?
Yes, sir. Yes.
Okay. So I welcome you all whoever is attending this talk. I am Rajiv Ranjan from IC Bangalore, working in Department of Materials Engineering. The title of the talk is a New Development in Ferroelectric Based Piezoelectric Materials. Now, since this is not a kind of conference, so rather it's a workshop, short-term course. So I'll be focusing mostly on the fundamentals of what makes these advanced piezoelectric materials perform so nicely. And of course, towards the end, I will highlight some of the interesting recent developments that has happened in the field. Why my slide is not moving? My slide is not moving.
सर आपका कर्सर एक ना होल्ड करके रखा हुआ उसने आपकी स्लाइड्स को.
Is it? Okay. Now it's moving. Yes.
Yeah.
So this is the outline of the talk. I'll talk about the basics of piezoelectricity. Then I'll talk about why ferroelectric based piezoelectrics are very interesting. Then some aspect of the important piezoelectric materials which belongs primarily to the perovskite family. And then what are the important considerations and factors which makes these ferroelectric materials give very large electromechanical response. And in the end, I will touch upon some of the recent developments that has happened in the field. So just starting, piezoelectricity, all of you have read in your textbooks what piezoelectric effect is. It's basically two effects. One is direct effect, another is called converse piezoelectric effect. The direct effect is when you press a piezoelectric material or you apply a stress, the surface develop a polarization. And in the linear field regime, if the signal is weak, then there is a proportionality relation between the polarization and the stress. And the proportionality constant is D, which is called the piezoelectric coefficient. When you do the measurement in direct effect type measurement, the unit of D you get is picocoulomb per Newton. The same material, if you apply electric field strains, it develops strain. And again, the strain is proportional to the electric field. And it is the same D here in this second equation, which is the piezoelectric coefficient. This phenomena is converse piezoelectric effect. And the D, which usually is given in terms of picometer per volt, one can verify very easily that the picocoulomb per Newton and the picometer per volt essentially have the same unit dimensionally. Also, thermodynamically, they are the same constant. It can be proved. Now, there are many applications just listed here. Pressure sensor, accelerometer, energy harvesting from vibration, spark generation. As Kiran was mentioning, in your kitchen, you have this spark you generate for lighting the gas stove. It has a piezoelectric material inside. And the converse piezoelectric effect has also been used in many different applications like actuator, very small displacement, very precise and small control, precise control of small displacements, transducer, as in sonar system, ultrasonic motor, etc. Now, this phenomena was discovered in 1880, of course, by these two brothers, Pierre Curie and Jacques Curie. So it's more than 140 years old. The phenomenon was discovered 140 years old. It was first discovered in a single crystal of quartz, tourmaline and roche salt. And this is just a list, just to give you a glimpse of where these materials are used in many different kind of application. It's taken from some textbook. I have given the reference from which I have taken. Right. So the list goes very long. Now, this is just to emphasize that these piezoelectric materials are used in wide-ranging application, and the current market share of piezoelectric materials is about $25.1 billion. This was last year's result, and it's still, there is some background noise. Somebody should mute the.
I request all the participants kindly mute yourself.
Thank you. So the market share is still growing because the application is still growing in this area. So it's very interesting, very technologically very important. Coming back to the fundamentals, direct piezoelectric effect, which is polarization proportional to the stress. Here, stress is represented by capital X. As you know, polarization is a vector, so it has 3 components. Stress is a second rank tensor, so it has a 6 component. And D is then coupling these 2 vector and this second rank tensor. It has 18 components. D11, D12, and so on. It's a basically third rank tensor, but I will not go into the detail. It's basically D1 is basically D111. It has 3 indices. So basically 27, but because of some constraint of the symmetry of the stress tensor, etc., 27 reduces to 18. You can go and discuss these things are discussed in a very well known book by called JF Nye, properties of crystalmetry and properties of crystal, JF Nye. Similarly, the converse effect also has this D coefficient, which is 18 coefficient in the matrix. Now, so it's not just a scalar quantity, it's a very complicated tensor quantity. So if you identify all these 18 elements, basically, then you know what is the total property of this piezoelectric material. But you don't have to go for all to determine all the 18 coefficient, because piezoelectricity is one such property which has very, very intimate relationship with crystallography. In fact, people earlier days people used to find out whether a material is centrosymmetric or not by measuring its piezoelectric, whether it's giving a piezoelectric signal or not. So there is such intimate relationship. So all of you are perhaps aware that there is something called 32 point groups in crystallography, 7 crystal systems, 32 point groups, 230 space groups. I think these are terms these are things which are familiar to you. And now the piezoelectric effect is related to this point group symmetry of the crystal. So of these 32, 11 has a center of inversion symmetry. It means that if you have an atom at XYZ in that unit cell, and if there is an origin, then you all expect the same atom at minus X minus Y minus J. So such crystals have a center of crystals are called said to have center of inversion symmetry. So 11 of these 32 point groups have a center of inversion symmetry. Only the 21 doesn't have a center of inversion symmetry, which is tabulated in this table. Now there is something called Neumann's principle, which all of you know that the physical properties of crystals are anisotropic. It means that if you measure the property in one direction, and if you change the direction of your measurement, the property will not be the same value. So this is called anisotropic property of crystals. Now there is something called Neumann's principle, which is a very, very bold statement, a very, very huge significance of this statement. It says that a symmetry of a physical property of a crystal must include the point group, which we have just discussed, point group symmetry of the crystal. Now, if you apply this statement to a piezoelectric equation, which we have just discussed below, which has 18 coefficients, and include and impose the symmetry constant of that crystal, on which you are going to examine whether how many independent piezoelectric coefficient you expect. It turns out that for the 11 centrosymmetric point groups, all the coefficients turns out to be 0. It means that these crystals which have center of inversion symmetry will not show piezoelectric effect. This is a very important prediction from point group perspective. So among the 21 remaining, which doesn't have a center of inversion symmetry, one also point group 432 also shows all the piezoelectric coefficients to be 0. So you are left with 20 non-centrosymmetric phase group. So all crystal belonging to this 20, one of these 20 non-centrosymmetric point group are expected to show piezoelectric effect. Now, whether you see it or not, that's a different issue, because the measurement sensitivity also plays a role. If you don't measure a piezoelectric effect or coefficient, it doesn't mean that the crystal have a center of inversion. Maybe it's so weak that you can't measure it. All right. So now this 20 centrosymmetric, non-centrosymmetric point group is divided into further 10 in 10. One is called the pyroelectric, which has a unique polar axis, and the remaining 10 doesn't have a unique polar axis. Like, for example, quartz, the material in which the first piezoelectric effect was discovered, quartz doesn't have a polar axis. So it's a non-centrosymmetric, but also it doesn't have a polar axis. Whereas the remaining 10 are piezoelectrics, we also have a polar axis, like barium titanate, which we're talking about. It has a unique polar axis. Now, and if you're able to change the direction of this polarity of the crystal, then the same material is said to be ferroelectric. So if you are unable to change, still it's a polar, it has a polar axis. It will be called a pyroelectric. So pyroelectric and ferroelectric are essentially the same, except for the fact that in the ferroelectric, you are able to turn the direction of the polarization by electric field. In the other case, your electric field is not sufficient to turn the direction of the polarization. So both materials exhibit change in the polarization when you heat it. So P as a function of T, and this phenomena, polarization dependence on the temperature, is used to make devices like infrared detectors. Whereas the ferroelectric ones can also be used as infrared detector, but mostly we know it most popularly for piezoelectric application. So this is just to show you of the remaining 20 point groups which have non-zero piezoelectric coefficient. This is just a list of this. This is taken from the book in the appendix of the book JF9. You can go through this. You can see only for the triclinic point group 1, which is basically no symmetry, you have all the 18 coefficients independent. So if you have a triclinic piezoelectric crystal, you have to determine, it's a Herculean task to determine all the 18 coefficients, kind of measurements you have to do, experiments. But as you increase the symmetry from triclinic to monoclinic, symmetry is increasing, further increase in symmetry when you go to orthorhombic and so on, rhomboedral and hexagonal, tetragonal. As you go on increasing the symmetry, the number of independent piezoelectric coefficient in that matrix decreases. For example, for the tetragonal barium titanate, which we'll be talking about a bit detail, it has only 3 independent piezoelectric coefficients: D31, D33, and D15, which you can see, which I have enclosed in this box to highlight this. The same is true for this hexagonal symmetry, point group 6 mm, and also for a ceramic, which is poled. Poled means you apply very strong electric field to a ceramic pellet, then it is poled. So that poled ceramic also behaves like piezoelectric, which I'll explain in a bit later. So all these poled ceramic, tetragonal 4 mm or 6 mm, they have only 3 independent piezoelectric coefficients. So these are if you determine all these 3 piezoelectric coefficients, basically you know the entire piezoelectric property of that crystal, or that poled polycrystalline ceramic. Now, what is D31, D33, D15 means is just a schematic. D33 means that you are applying force along some axis, and you are measuring the polarization developed perpendicular to that axis along which you have applied force. So the direction in which you measure the polarization and the force is the same. So this 3 means along z direction. D31 is that you are stretching it along or compressing compressing it along, let us say, y-axis, and you are measuring the polarization along the z-axis. So this is D31. It's called transverse piezoelectric coefficient. In that sense, D33 will be called longitudinal piezoelectric coefficient. And the one D15 is basically shear piezoelectric coefficient. Basically, you are shearing the crystal and then measuring the polarization develop on the surfaces. So all these three coefficients are very important to determine the overall piezoelectric property of your pole ceramic or single crystal. The complete piezoelectric constitutive equation also involves not only the strain and polarization, but also because when you apply a stress, the material is bound to develop a strain, so you can omit that. So this takes care of this. So strain is proportional to stress, which is more or less is the compliance, and the second part is of course the piezoelectric, which I've already discussed. Similarly, the dielectric displacement, we all know for any dielectric D is equal to epsilon naught E, that is taken in the second term in the second line, but also if the material is piezoelectric, you have this piezoelectric coefficient also coming into picture. So this is the complete constitutive equation. So you see that dielectric constant and compliance, elastic compliance also comes into picture when you write the complete equation, piezoelectric equation. And they affect the property, overall piezoelectric property, electromechanical property as well. So these new terms comes into picture, which is permittivity and elastic compliance in addition to your piezoelectric coefficient D, right? Now elastic compliance also depends upon the symmetry, etc., etc. The D33, as we have said, all depends on the symmetry. For a pole ceramic, you have D31, D15, D33. For a pole ceramic, the number of independent dielectric constant is only 2. K11, which is the longitudinal and the transverse direction, perpendicular to this pole axis. So these are the total number of independent coefficients you have to analyze when completely analyzing the piezoelectric property or electrical mechanical property of your piezoelectric material. So just to emphasize, without going into the detail, piezoelectric property of the material also depends upon the elastic compliance, not only the small d, which is piezoelectric coefficient, and also the dielectric constant. In a subsequent equation, I will show you how they are interrelated. But before I go there, I'll just talk about what are the important figure of merit for piezoelectric materials. D, we have just discussed about piezoelectric strain coefficient, which is strain is proportional to the electric field, the coefficient is D. That's what we have started with this talk. So this is fine. This is one figure of merit, and this figure of merit is important for actuation application. Then there's a piezoelectric voltage coefficient G, which is not related to the piezoelectric coefficient D. If you have the D piezoelectric strain coefficient divided by the permittivity, epsilon naught epsilon, then you get the G value. So this is important for sensor application. The higher the G, the higher the better it is for sensor application. Not only sensor application, but also energy harvesting. People are now using piezoelectric materials. That you from the vibration, you generate the charge, which you use and store it in battery to generate energy. So to generate energy, you need high D value. It means that the permittivity of your material should be low and high D, and the piezoelectric coefficient should be high. So this is important one. Then something called electromechanical coupling factor. This third piezoelectric figure of merit, which is essentially the kind of ratio of electrical energy converted to mechanical energy divided by the input electrical energy, or vice versa. And the K square is proportional to, as you see the last. Please mute, please. Please ask people to mute.
Kindly mute your mic. I request all the participants kindly mute your mic. Otherwise, I have to remove someone.
Thank you. So this electromechanical coupling factor which is basically a kind of transduction phenomena, conversion of energy from mechanical to energy, and it's a dynamic. This is important figure of merit when you are looking for a kind of like ultrasonic motor, for example, or sonar device. You generate wave. So basically, this is the important figure of merit if you want to generate wave using a piezoelectric material. So this K square is proportional to D square. D is the piezoelectric strain coefficient. Epsilon naught, epsilon is the permittivity. S, you can see here, is coming into picture, which is the compliance in the denominator. So this is where which is a very important figure of merit for energy conversion from mechanical to electrical or electrical to mechanical. This is very, very important. So it depends upon all three quantities: the piezoelectric strain coefficient, the permittivity, and the compliance using this expression. Now, because you have different kind of D values, so correspondingly you have different kind of K values. Because D3, as I said, there are three important D types for a pole ceramics: D15, D33, D31. Correspondingly, you have K33, K31, K15. This just for complete mistakes, I mentioned this quantity. Now, once you have generated a wave, you want the wave to be transmitted across the medium. For that, you have another figure of merit, which is called acoustic impedance. Like in electrical impedance, you have the acoustic impedance. So for efficient energy transfer, you want this acoustic impedance to be as good as possible. That depends upon under root rho by rho into C. Rho is the density of the material and C is the elastic stiffness. So you can know, if you want to have, for example, if you want to transmit this wave in water, water has a very low density. So unless your material has a low density, you can't transfer the wave, the energy efficiently into the medium. So you will look for a material which has a very low density comparable to water. Of course, you cannot have water like density in a piezoelectric, but try your best to match this acoustic impedance. So these are the important figure of merit which I have I highlighted, which you must keep in mind depending upon what is the device you are going to make out of this piezoelectric material. Now these are the very, very fundamental things which I discussed about piezoelectric material. I talk about ferroelectric based piezoelectric material. As I said, quartz was a material which is not a ferroelectric. It's only piezoelectric material, right? Now, all the advanced piezoelectric materials which we see nowadays is all based on ferroelectric materials. So the question arises, why ferroelectric materials give such nice or very large piezoelectric coefficient? Just to give you an example before I go, which perhaps will come in one of the slides. For example, the quartz has a piezoelectric D value of 2 picocoulomb per Newton, right? And you require a single crystal quartz. Whereas a barium titanate, simple barium titanate, you make a ceramic, fire it, just pull it, apply strong electric field. It shows a D value of 190 picocoulomb per Newton. You see the difference. A ceramic which is so easy to make, you don't have to make a single crystal, make it, densify it, apply strong electric field. It gives a D value of 190 picocoulomb per Newton. Whereas quartz, you need a single crystal quartz. How difficult it is to make a single crystal, you can imagine. That has only 2 picocoulomb per Newton. So definitely you would like to ask, what is so interesting about these ferroelectric materials that give such large value of piezoelectric coefficient? This I'll try to highlight in some of the remaining in these slides. Just I'll take some water. Now, so let's go back to ferroelectricity. What is ferro? Again, this textbook everybody knows is whosoever have studied physics. Ferroelectricity. So you know, if material is ferroelectric, if you do PE cyclic measurement, you get a hysteresis, as shown here. It's similar to the ferromagnetic hysteresis with x-axis as magnetic field, y-axis as magnetization. In fact, it's so coincidental that ferroelectric, though has no iron, the material which was discovered, ferroelectric, has no iron, but it was given the name ferroelectric because of the similarity of the PE loop with that of the MH loop. So So, but once it is given the name, it sticks, it stays. So you can't do anything. So we have to use. So ferroelectricity is associated with this P loop, which is reversible P loop. So why this P loop shows like this? You can just go by the analogy of ferromagnetic material. Whenever you see a magnetic hysteresis like this, you have in mind that there is domain-wise motion. In the magnetic case, you have the magnetic domains which are moving when you apply magnetic field, and they are tracing a hysteresis. It's not reversible. It doesn't reverse the same path during the increasing and the decreasing field cycle. That's why you have the hysteresis. Now, why domains form in ferroelectric crystal in the first place? The domain form, one important reason is electrostatic. You are all aware of the D equals to L naught plus P in dielectric, and also the second equation, divergence D is equal to rho. These are all famous electrostatic equations. Now, if you take the divergence of D in the first equation and then to take the second equation, you get finally divergence of E is equal to rho minus divergence of P, right? It means where rho is the free charge density in the material. Now, if you are talking of a very nice insulating material, you don't have free charges there. So that is 0, rho is 0. So divergence of E is minus divergence of P. Now, this is true for any dielectrical as well. But what is important in ferroelectric, that P is a spontaneous polarization. You don't apply electric field to get P there. Unlike in normal dielectric, you get a polarization that is called induced polarization only when you apply electric field. But this in ferroelectric, the polarization is self-induced, right? That is given the name PS. PS means spontaneous polarization. So because there is spontaneous polarization, and if the spontaneous polarization is diverging at any space in the material, then you get a divergence of E minus value. It means that there is a depolarizing field which comes into picture whenever there is a divergence in the polarization. Now this is very important. Now, where you get that, suppose you have a single crystal, where you get the divergence in the polarization? Definitely at the surface, because your crystal has a finite size, you have a surface. So, you leave the crystal, outside the crystal, there is no polarization. So, the polarization is not continuous. That's why you have a divergence of P at the surface. So, the discontinuity or the change of the polarization at the surface creates a depolarization field which opposes, with the direction of which is opposite to the direction of spontaneous polarization. The minus sign is that opposite direction. Now, this depolarizing field is such that it will try to oppose the polarization itself because it is created by the divergence in the polarization. It tries to suppress the polarization. Now, to minimize this depolarizing field, the crystal breaks into domains, as shown in the right side here. So you have a up arrow means in this region of the crystal, all the polarizations are up. You have right side. In this region of the crystal, the polarization is on the right side, down, left, and so on. So the overall polarization of the crystal, if it's arranged like this, then you have a net zero polarization of the crystal. If you have a net zero polarization of the crystal, then the depolarization field is very, very small. So the depolarization field, so the domains are formed to minimize the depolarization field, which occurs because of the divergence in the polarization. Now, this surface is one part, but there can be divergence in different places. If there is a heterogeneity in your case, like grain boundaries, if you have polycrystalline material, grain bound one source of depolarization. Your polarization is not continuous; it's changing across the grain boundaries. So there are many sources of depolarization field, and that in turn gives rise to the different configuration of domains. I'm only touching upon essential ideas. The details vary from material to material and system to system. Just a moment, stuck. Yes. Now, this is just a kind of glimpse to show that ferroelectric materials are not interesting only from the piezoelectric point of view, but there are many different applications of ferroelectric material. Infrared sensor I just touched upon because the polarization also depends upon temperature. You can have infrared devices based on this ferroelectric random access memory, because the polarization can go plus, minus, and so on. So it can be used in memory devices. Nowadays, people are also playing with ferroelectric material for piezocatalysis, photocatalysis, piezocatalysis, photovoltaic effect. These materials are also being used in solid state cooling devices, electrocaloric effect like magnetocaloric, where you can have large electrocaloric effect at room temperature, and the device can be very small because there is no magnetic thing involved here. Just electric field across a pellet, and you are able to cool. Of course, there is another interesting phenomenon called magnetoelectric effect. When the polarization couples with the magnetization, you can just change the magnetization by applying electric field and vice versa. So many different applications. I'll not go into that, just give a picture of how interesting these ferroelectric materials are from different perspectives. Now, so it happens that this year is the centenary year of ferroelectricity. The phenomenon was discovered in 1921 by J. Walasek in single crystal of Rochley salt. Right? This is a picture showing this transparent crystal. Is a Rochley salt crystal. It's a water soluble. So basically, if you have a water soluble material, it means it will be microscopic. You cannot use in devices because it doesn't have a longevity. So the most important incident which happened in the field of ferroelectricity is the discovery of ferroelectricity barium titanate during the Second World War, 1944. Nobody gets the credit because it was almost discovered simultaneously by different groups in Japan, USA, Russia, Germany, etc. Because it was very highly secret things. People were preparing materials for war and for the defense, respective defense of the country. So it was secret activity, not a scientific activity. So nobody gets credit for discovery of barium titanate, but different groups discovered simultaneously. But this is more important because it's now an oxide, unlike the previous cases, Rochley salt and KS2O4, they are all hygroscopic. It's a ceramic which you can easily make in any form you like. So figure shown here, different shape of ceramics. So you can apply standard ceramic technology to make this material. Basically like give a shape, heat it at high temperature, you get solidified, material is ready. So it's such easy. So these are, and you can make them, it's all polycrystalline, right? So this discovery make the ferroelectric material very, very important because you can make it very easily. They're robust in the sense that they can withstand harsh environment like humidity, etc., etc. This is a landmark thing which happened in the Second World War. Okay, this is just, I talked about how this discovery is important. Even a small pellet of barium titanate has a piezoelectric coefficient of 190 picocoulomb. Quartz, on the other hand, a single crystal is required. You get picocoulomb, D value of 2 picocoulomb per Newton. Of course, quartz is not ferroelectric. So if you do P measurement of quartz, you will get linear line, just like in normal dielectric material. Whereas if it's a ferroelectric, even if it's a polycrystalline or single crystal, you get a nice P loop. Now, this PR is called remanent polarization, similar to your magnetization. Now, because this remanent polarization, even if you have decreased the electric field to 0, that is what makes this material pole. So you apply strong electric field across the pellet, and then you have removed the pellet. Still, you have a remanent polarization PR. So the material is the whole material, which is polycrystalline in nature, which have different grains oriented in all different directions. Still, you have net polarization of this material. That is why these polycrystalline ferroelectric materials behave like a piezoelectric material. Now, there are many different category of piezoelectric materials from the crystal structure perspective: tungsten, bronze, perovskite, pyrochlore, layer structure, etc. But the one which has attracted most attention is this perovskite material, APO3. Very simple looking structure. I'll just spend some time on this one. Now, perovskite structure is very simple, as you have seen. The blue ones are the A atoms. The green at the body center position is the B atom, and the red one is the oxygen atom. AbO3. So this unit cell has one formula unit of AbO3. O is written X here, but X is an anion. In our case, it will be oxygen. Anion will be oxygen. Okay. Now there is something called Goldsmith tolerance factor T, which determines which gives a kind of relationship. What should be the respective size of A, B, and X so that the material can form a perovskite structure. So if this T lies in the range of 0.7 to 1.1, then the material is likely to crystallize in perovskite structure like this. But if it is even in this range, you have a subcategory. If it is less, if it is in the range 0.9 to 1, it will be tetragonal cube. If it is less than 0.9 and between 0.7, then the material also have octahedral tilt. Now, what is the octahedra? You can see the same material, same structure can be viewed in two ways. The first way I have already explained. Below one, you see I have emphasized on the octahedra. For example, the octahedra is also shown in the top figure here. But here, if you look at the down figure, it's the same structure, only the outline is changed. And you can visualize the same perovskite structure as corner octahedra with the 8 sitting at the center of this 8 octahedra. Okay, it's the same structure, but just viewed it from a different perspective. Now, I assume some people are physics background, so just I like to highlight from this slide the kind of distortions you expect and some of the distortions are ferroelectric. Now, the ferroelectric distortions of this perovskite is the one which is shown on the left here. They correspond to zone-centered distortion. Now, this is zone-centered means this is a kind of a K space in which Kx, Ky, Kz is the reciprocal space. Origin is the gamma, right? So if your cube tetragonal like this one, the polarization is along one of the cube axis, then it's tetragonal distortion. It can also happen the polarization, the titanium ion is displaced along one of the body diagonal, like in this case. Then it takes a rhomboidal structure. In both the cases, tetragonal rhomboidal shown in this figure, the number of formula unit per unit cell remains the same as in the cubic case. So one formula unit of AbO3 here as well as here. So such distortions are called ferrodistortive transitions. The cube becomes tetragonal. The number of formula unit per primitive cell remains the same. Such transitions are called ferrodistortive transition. Okay, the octahedral which I discussed about is also one of the most common distortions which you encounter in perovskite material. They can be classified into two important categories. One corresponding to R point distortion. R is this point which is shown here. Is 111 along the reciprocal space. Basically half. K equals to half is shown written here. So this point is called R point distortion. And if this distortion happens, you will find that the two neighboring octahedra along the tilt axis or the rotation axis are rotated in opposite direction. We call it anti-phase octahedral tilt. The top octahedra is rotated in the clockwise, the bottom octahedra is rotated in the anti-clockwise fashion. Right? It can also happen that the octahedral tilt rotate in the same fashion, both up and down. Both octahedra rotate in the same direction. Both are, for example, clockwise, anti-clockwise in this bottom figure here. This also rotate anti-clockwise, this also rotate anti-clockwise. Right? In both the cases, the number of formula unit per unit cell is changed from the cubic structure, and that is why it is called anti-ferrodistortive transitions. All right. So these are important transitions which also you encounter in ferroelectric system, or the ferroelectric system. It so happens that the ferroelectric Fe and the antiferrodistortive transitions sometimes compete, sometimes collaborate, and have a dramatic influence on the overall polar property of your material. If one is working in ferroelectric ceramics, one needs to be aware of what is important structural distortions which might be possible, and they change the overall property. For detail, if somebody is interested in octahedral tilt, I refer to this original article by A.M. Glazer and the subsequent article by Howard and Stokes. They can refer to these papers to know more about what are the possible tilt systems which is possible in perovskite structure. Now, coming back to the ferroelectric case, and in the context of perovskite, now I'm not talking general, I'm talking in the context of perovskite material, like the barium titanate or lead titanate or strontium titanate. Now, when you heat this, if the room temperature is ferroelectric, when you heat this material beyond a certain temperature.
Rajiv sir.
Yes.
Rajiv, can I stop for a minute? Sir, there is a one box appearing, maybe that is related to the team setting. It is coming in your slide. Is it possible to move it from the PPT? Maybe it is the control panel of this Microsoft team.
Okay, sir.
Okay, yes. Thank you.
Thank you, sir. Thank you.
Okay. So, when you heat it beyond certain temperature, it becomes paraelectric. Okay. So, let us say at high temperature, some high temperature, definitely a ferroelectric material will be in a paraelectric state. The temperature depends upon the material to material. For barium titanate, it's 120 or 130 degrees centigrade. If it's lead titanate, that is about 490 degrees centigrade. Okay, then let us not worry about that. Beyond certain temperature, they will be paraelectric, and that paraelectric state is a cubic. Has a cubic structure, which is central symmetric in nature. So below the Curie point, it becomes ferroelectric, and in this case, I am indicating that the cube has transformed to a tetragonal with the polarization direction along the 001 axis of the cube. And the P is the polarization direction. Now, there are two important things. Definitely, paraelectric to ferroelectric transformation, you have a spontaneous polarization which is developed. Second important thing to take note of is not the strain which develops in the unit cell. That is also spontaneous lattice strain, similar to the spontaneous polarization which develops at the Curie point. The material also develops a spontaneous lattice strain. For example, if it's tetragonal, the way to make the lattice strain is C by A minus 1. C is along the C axis, A n equal to B. For tetragonal, you can always measure C by A minus 1. If you do X-ray diffraction, you can get the lattice parameter and you get. So for lead titanate, this C by A minus 1, which is the tetragonality, sometimes refers to tetragonality 6%, very large, 6 times large than in barium titanate. Now, why this spontaneous lattice strain happened? So before that, one thing you have to keep in mind that a ferroelectric to paraelectric transformation is not only changing the polar state of the system, but also it's in the state. So the structure and the polar are intimately linked in a ferroelectric material, right? Now, theory says that this change in the development of lattice strain in the ferroelectric state is piezoelectric phenomena, which is the polarization developed when you apply stress, or strain is developed when you apply electric field. These are the basic. We started this lecture with those phenomena of piezoelectricity. Now, so that is a linear effect. It means that if you change the direction of electric field, if you make it negative, the strain can be negative, right? But electrostation is square dependence of the strain is proportional to polarization square. It means that it's a quadratic relationship. It means the spontaneous strain will always be positive, irrespective of whether you change the direction of or sign of P or not. It's always positive. Now, this is a very fundamental. Now, electrorestriction doesn't require any kind of this group theoretical argument. Of course, if you want to know the anisotropy, you have to apply that. But electrorestriction is always present in any material. You don't need have a centrosymmetric or non-centrosymmetric. All you need that it should be an insulator. It should sustain electric field, right? So this is very fundamental, more fundamental than the piezoelectric thing. So if your material has developed polarization, because of this electrorestriction, it's bound to develop strain. So this is how people explain this strain, which develop the spontaneous strain in ferroelectric via the mechanism of electrorestriction at the unit cell level. Now, electrorestriction is a fourth rank tensor because you have a lattice strain, which is second rank tensor on the left hand side. P square is Pi Pj, again 2 indices, so 2 plus 2 is 4. So it's the fourth rank tensor, more complicated to deal with. Okay, now let us talk more about this strain, and here with this simple slide, I'll try to give you some kind of feeling about what are the important parameters to make, which makes the piezoelectric, ferroelectric material gives very, very high value of piezoelectric coefficient. So we just discussed about this electrorestriction phenomena. Strain is proportional to P square, right? P is the polarization. Now, this small derivation I have done here. Now, if you have ordinary dielectric, which is not ferroelectric, then P equals to chi E, right? The strain is proportional to Q chi E square, right? So this is just for any ordinary dielectric. But if it is a ferroelectric, the dielectric is also ferroelectric, then you have, when you apply, there is already a spontaneous polarization without your application of electric field. When you apply electric field, you also have an induced polarization. So the total polarization is induced plus spontaneous polarization. So now you apply the electrorestrictive argument here, strain proportional to Qp square. In the end, you find that the strain has both induced polarization, spontaneous polarization, and chi also come into picture. Now, induced polarization is very, very small compared to the spontaneous polarization in ferroelectric. Very, very small. So you can ignore the first term here. This term you can ignore. Then you have Qp square, and then this one. Now, Ps is a spontaneous polarization, which is something fixed. You can't do anything. This is constant, right? So if you take the derivative of strain as a function of electric field, what you get is this quantity. This is very important. Twice Q chi Ps. Very simple derivation, but very useful one. Now this strain is proportional to electric field. You can see here. Then what is the coefficient here? That of course has to be the D coefficient, the piezoelectric coefficient, right? That's how you define the piezoelectric coefficient. Now you have a relationship which suggests what are the fundamental factors which determines or controls the piezoelectric coefficient in a ferroelectric materials. That is, the piezoelectric coefficient is dependent upon the electrorestrictive coefficient Q, the susceptibility, dielectric susceptibility, and the spontaneous polarization. So if you have all this quantity very large, you expect the ferroelectric material to have very large value of D. So this tells you why ferroelectric materials have large value, because you can definitely, there is PS, which is large value. Sometimes you can increase the chi value beyond the PS. You can further increase. Sometimes also you increase the Q. In the next few slides, I will show how these material designs strategies have taken advantage of this understanding of the dependence of piezoelectric coefficient on the Q, chi, and PS. PS, of course, is known, but rather on Q and chi. Now, it's just a schematic of your piezoelectric and electrorestrictive. Anyway, you know this. One was quadratic dependence. For electrorestrictive, piezoelectric is linear. Anyway, now, how can you either increase the chi value or you increase the Q value? I'll take both cases one by one. Now, Q, the material, the ferroelectric material, if you take barium, it will have some Q value. Take any material, it will have some Q value. Now, how can you increase the Q value? Now, recent studies have shown that the Q value of something called relaxer ferroelectric is higher than normal ferroelectric. Now, what is relaxer ferroelectric? Normal ferroelectric is given here on the left side of the box. Here, if you do temperature as a function of dielectric constant, it is sharp peak, and this peak it doesn't depend upon the frequency of your measuring signal. Whereas relaxer, you have a diffuse peak, not very sharp, and the peak temperature varies as a function of frequency. It increases as the frequency of the signal increases. So this is a very typical characteristic of relaxer ferroelectric. If you look at the microstructure, the normal ferroelectric have well-defined domains, like here in 90-degree domains, which is discussed about, right? Reasonably big micron-sized domains, and they show P square is P loop. These are typical characteristics of ferroelectric. Whereas if you have a relaxer ferroelectrics, these domains are not so well defined. They are very small in size, of the nanometer size. They are often called as polar nanoregions. And if you do P measurement of such material, relaxer material, you get a very, very slim P loop, very, very slim P loop, right? No, so it has been argued, or it has been observed, that the relaxer ferroelectric material often exhibit higher Q value, higher electrostatic coefficient compared to normal ferroelectric material. So if you induce in a ferroelectric material some relaxer features, how you can do that? So we know how to do that. So basically, you want to break these big domains into small domains, but still retain an overall ferroelectric polar property. So you put some dopants in the material which suppresses ferroelectricity here and there, right? So if you increase the disorder here in the sense that the polarization is truncated by that additional element which you put in your matrix, then the disorder increases, and then a normal ferroelectric can transform to relaxer ferroelectric. So when it happens, the free energy of change in the polarization, this is shown by this free energy function as a function of polarization, the energy barrier from one state to going from one state to the other state decreases when there is a disorder in the matrix. So when the energy barrier is decreasing, it's easy for the polarization to switch from one direction to other direction, right? So when you have high Q value, when the Q value increases, the Landau energy level becomes shallow. It means the barrier height decreases, and that leads to enhanced polarization switching. Now, enhanced polarization switching was first discovered in PJT, which is the well-known phase of piezoelectric material. Now, this is a solid solution of lead zirconate and lead titanate. On the right side, lead titanate. In this diagram, you see a red line, which is called the morphotropic phase boundary, which separates a rhombohedral phase region from a tetragonal phase region, this side, right side tetragonal. So there is this boundary basically is an interferroelectric instability, because rhombohedral is also ferroelectric, tetragonal is also ferroelectric, but the crystal symmetry is different. In one case, tetragonal, the polarization is along the C-axis. In the rhombohedral, the polarization is along the body diagonal. So polarization is changed. So at the boundary, if you have a composition at the boundary, there is an instability in the polarization, and at those instability, the piezoelectric coefficients are further improved, right? So this becomes a kind of material design criteria that you allow something such as to get a morphotropic phase boundary like situation, and you get enhanced piezoelectric. Now, question is why morphotropic phase boundary improves the piezoelectric coefficient? We go back to this equation which we have just derived in a very simplistic manner, that the piezoelectric coefficient is a function of Q, P, and chi. Chi written here is the same thing, permittivity. Chi is susceptibility and permittivity are related. Chi one is plus one is there, right? Chi equals to epsilon plus 1 or minus 1, I don't remember, but don't worry about that. Now, here it has been shown that the D31 is proportional to epsilon 3, means the permittivity, longitudinal permittivity. D15, which is the shear piezoelectric coefficient, is proportional to this epsilon 1, which is transverse permittivity. It so happens people have determined theoretically using experimental parameters that when you approach the MPB, the chi11, which is the transverse permittivity, it means that you are applying, you have pulled the material in z direction, but you are measuring the permittivity in the x or y direction. That is transverse permittivity. So the transverse permittivity increases abruptly near the MPB composition. So if the transverse permittivity, this value increases substantially, then your D15 is going to increase dramatically. Now, this is important. So when you have a polycrystalline material, your grains are, you have no control over the orientation of the grains. Some of the grains are oriented in very, very different direction than the spontaneous polarization direction, right? So when you apply electric field perpendicular to the pellet thickness, I'm using my hand here, but if it was a physical, I could have give you a feeling. The polarization is basically tilted away from the thickness direction, but you are trying to orient along the thickness direction when you are applying electric field. So that is basically you are increasing. If the psi11 is high, it is easy for the polarization to rotate away from the spontaneous polarization direction. So that gives rise to very high D33. This explains why MPB compositions gives very large D33 value by virtue of very large shear coefficient of the individual ceramic, of the individual grain in the ferroelectric ceramics. Now this translates into the same picture. This is the same picture that the polarization, which is, let's say, if you are tetragonal, and if you are at the MPB, close to the MPB, the system can easily rotate towards away from the C axis. It can go towards the R direction and follow a trajectory. It can go towards O direction and follow a different trajectory and so on. So this is shown in this free energy diagram, essentially, which says that the free energy profile becomes quite flattened, as a consequence of which it is easy for the polarization to rotate from one direction to another direction. It's the same thing. I'm just talking in a different language. So the essential picture is when you are at the MPB morphotropic phase boundary, because of the ferroelectric instability, the system has this tendency to orient away from the polarization direction, spontaneous polarization, more easily than to just stretch its polarization along the polarization direction itself. So that is essentially the picture which I want to convey, which is responsible for the large electric field. Now that is one picture, but I have not talked about what the domain wall has to play all this. I have just talked about a single crystal and a single domain. But domain walls are essentially there in any ferroelectric material, particularly in ceramics. You will definitely have a domain walls. As I said, domain wall form because of this electrostatic consideration. And once the domain walls are formed, the domains are pinned basically by the defects which are already present in the material. This is schematically shown in this figure, that because the defects are all randomly located in the material, so randomly the domain wall pins. Some defects pin the domain wall more strongly than the other defects. That is represented by the different height of this barrier here, depth of this barrier here. So if the domain wall has to move, it has to get rid of that pinning from that defect. So you have to apply electric field. So basically it has to move out of this barrier and go on to the other barrier. So that is how the domain moves. So it's like a motion of domain walls can be likened to a motion of some body in a viscous medium, right? Because the pinning centers make the whole thing viscous. Now, so their motion contributes to your dielectric, ferroelectric, and the piezoelectric properties. Now, just this slide shows you about how you can control the domain walls and their domain density. So if you have free charges, for example, this is the electrostatic equation we discussed, rho, then it can compensate to a large extent the depolarization field. So you can have a less number of domain walls because partly it is compensated by rho, but in most cases rho is 0, so no compensation, you have large number of domain walls. Now, domain wall is also dependent upon the size of the crystal. So this T is the thickness of this crystal. If you reduce the thickness of T, the domain width, basically how big the domain is, that also decreases. It decreases T to the power half of the crystal thickness. So if you decrease the same crystal, you expect the domain size to decrease, but since the volume, so basically you expect more and more domain walls to be formed, right? So the domain wall density increases. Also, when you are at the MPB, because it's lattice instability, your lattice becomes soft, elastically soft. So the sigma, which is here, is the domain wall energy. Because the lattice becomes soft, the domain wall energy also becomes small. So the system can afford large number of domains. So it means that D can become small. You can have large number of domain walls. So these are the factors, important factors. There are other factors which also control the domain walls and the size of the domains that eventually control. These are typical example of barium titanate, where you reduce the size from 1 micron, from 10 micron to 1 micron, and the dielectric constant increases dramatically from 2000 to about 6000. Not only that, if the piezoelectric coefficient from 190 I just talked about, it can go up to about 350. If the grain size is reduced to 1 micron. So this is all playing with the domain density, etc., etc. You can control the piezoelectric property. The point I want to highlight is that apart from this lattice instability, that you can control the piezoelectric behavior of the system or the dielectric behavior if you know how to control the domain wall or the domain density of the material. But the two domain wall motion and the lattice motion are not separate, by the way, right? So if you apply a electric field in a single crystal, basically you move the domains, and more domains are aligned in the direction of the electric field. The volume fraction of the domains aligned in the direction of electric field increases. That can be easily seen if you do a diffraction of a material which is under electric field, the relative intensity changes. And you also see that the peak position shifts. It means that there is a lattice strain which is developed. And they are very correlated. The more the domain orientation you find, the more is the peak shift. So there is a very strong correlation. People have done studies. We have also done studies on this one. So they are not completely different. Domain wall motion doesn't affect lattice. No, it's not the case. In ferroelectric, all are coupled. And this coupled phenomena determine ultimately your overall piezoelectric and electromechanical response. Now, I think this is what I have covered so far, is the essential concept which is important to know if you have to design a piezoelectric material with high electromechanical coefficient, right? So what are the things you have to keep in mind? Relaxer ferroelectricity further flattens. You have to look for a compositional design so that you get a interferoelectric stability and so on. You can increase the domain wall size, decrease the domain wall size by changing the size of your grains. All these factors comes into picture. So a good understanding of all these factors helps you to design a good piezoelectric material for the property you're looking for. Now I'll go to the final thing. Recent development in piezoelectric research. So basically they are guided by two important considerations: search for new materials with giant electromechanical response. Of course, it is known that ferroelectric materials, particularly the MPB ones, shows large electromechanical response, but people have achieved piezoelectric coefficient which was not imaginable until now, but these are recent. And of course, there are new functionalities people are working on based on piezoelectric materials like energy storage, optical thermometry. I'll just touch upon briefly upon one of these things in the remaining 15 minutes I have. Now, the PZT was the one which has dominated the market for quite long time because of its very large piezoelectric coefficient And there are some advantages of piezoelectric, like thermal stability, that even if you change the temperature, the value doesn't change much. It means that you should have, if you want to have a piezoelectric material which is thermally stable, it means that your Curie points would be far away from room temperature. Because if you are close to the Curie point and if there is any thermal fluctuation which happens in the device, your whole polarity will change, and so the device will not be working at the optimal condition which is it is set for, right? Okay, so PJT has all those interesting features, and that's why it ruled the market for since 1970s until now, still ruling the market. But consideration of health and environment has brought in regulations, which is one of these regulation is quoted here, European directives in 2003, which suggested that which wanted the industry to move beyond this lead base or toxic material and use non-toxic material. So it also influenced the piezoelectric ceramics, because then there was an urge to look for lead-free, because lead was the important one and lead is considered to be toxic, lead-free. So when this paper was published in Nature in 2004, the PJT were the ones which has very high D33. All you can see here, PJT, and the lead-free were having less than 200 picocoulomb per Newton that time in 2004, right? As if only PJT can show high D33. No, the lead-free like barium titanate or potassium niobate or sodium bismuth titanate, they are not interesting. But once this regulation comes into picture, and when this paper was published, this paper showed for the first time that sodium potassium niobates lead-free ferroelectric can also show a value which is comparable to piezoelectric, about 400 something was, and that too with very complicated textured ceramic formation, not just ordinary ceramic. They made it something textured. But this was the first step which suggested that even in lead-free, at least in this potassium niobate system, you can achieve very large value as comparable to PJT. This was the starting point which gave a lot of hope in the piezoelectric community that other lead-free compositions can perhaps also show such high value. And it did happen, as I'm going to show you. So after the publication of the paper, you can see the number of publications increasing exponentially. Now it's almost saturating. But you can see the tremendous surge in interest in lead-free electric ceramic, mostly in, again, restricting into this perovskite family, barium titanate, sodium niobate, potassium niobate, sodium bismuth titanate. There are very few, only countable 5-6 materials in the perovskite family which are ferroelectric. So people have to play around this material. You have to have a ferroelectric material to play around with the composition and other things to improve. Not much of choice, but to just play around with this material. Now, people have now shown that even that potassium niobate piezoceramic, even if you have non-textured, just make it, just by compositional design, you can get values what the Nature paper was reported. Now there is value even higher than this. I have here around 500 in this paper in 2014, right? So this is just by, you can see the chemical formula here. So much of element has been put inside. Now the problem with this, that even if one group gets such a large value, there's so much of element and they're so tiny here and there that if you just disturb another group cannot get this value. Right? It's a very complicated composition, and so the reproducibility is an issue here. Anyway, and in 2009 was another paper by a group in China and Japan which published that even a barium titanate based piezoelectric ceramics, which was the D33 was limited to 190 or 200 picocoulomb per Newton, can give value as large as 600 picocoulomb per Newton, right? 600 picocoulomb per. Now this is even beyond PJT by a less complicated than as in potassium niobate, zirconium and calcium substitution of barium titanate. So this was another landmark discovery. The only problem with this material is that its Q point is 80 or 60 degrees centigrade. Means if you want to work at room temperature device, where even a small fluctuation in temperature, it will spoil your device. So that is a major drawback of this material. You have to have some kind of cooling arrangement so that D33 doesn't change, but it's very difficult, not economically viable. So basically, if you want a material with high Curie point. Then another discovery happened that one of this material, sodium potassium niobate based material, shows a very large strain, electrostrain of 0.4 was this, 0.45. Later on, another group showed 0.7. Now, PZT based material has given a maximum strain of 0.3. Now, this is almost double the value, right? There is a scientific basis for this. I'll not go into the detail. I'll just highlight what are the interesting things that has been happening recently. So you have now material in the lead-free category, which shows extraordinarily high strain of 0.7%, which is almost double than what PZT-based material has shown. The benchmark of electrostrain, if we don't separate lead-free and lead-based, was in something called PZNPT or PMNPT. These are very well known in single crystal of this material. People have shown this is a paper in 1997, very old paper, but this is a very landmark paper published in JAP in 1997. Those were days when impact factor were not very of high consideration. People just published and they enjoyed publishing good papers. So this is a landmark paper which showed for the first time that a strain of such value, high value, 1.5% in a ceramic. Ceramics are brittle, unlike in metal, you can simply stretch it. Locations are there and they can move the material stretch. But this is ceramics. If you stretch 1%, it's too much. You can't, even if you stretch once, second time it will fail and it will fracture. But the very fact that you can stretch it that much is very interesting. Now, this material set the benchmark value of what is the electrostate cell 1.5% for some compositions. And the D33 was about 2,500. In the single crystal, by the way, this is not a ceramic, polycrystalline ceramic. This is a single crystal. So these materials have a D33 of 2,500, exceptionally large in single crystal and exceptionally large strain. If you make a ceramic of this material, the D33 will be around 600 degrees, 600 picocoulomb. And the strain will be much less than what you see in the single crystal, right? So of course, single crystal and polycrystalline have a different thing. In certain direction only you see this amount of strain and the D33, but if you change the direction of the single crystal, the number will be very different and much smaller. Polycrystalline, if you have a polycrystalline material, it's an average of all possible orientation. That's what you see as a property of the polycrystalline material. Okay, so now you have a new development in last year. We showed that a PMNPT, if simply modified by samarium, little bit of samarium, just 2%, and the single crystal of this gives a D33 of 4100 picocoulomb per Newton, exceptionally large. See, the previous one, this was the benchmark, which people knew that this is the maximum, 2500. Now, you are talking about 4100 picocoulomb per Newton. Huge value in single crystal. Now, that the same material when made in the polycrystalline form, which is very easy to make, right? We all make pellets, most of us, gives a D33 of about 1500 picocoulomb per Newton. Exceptionally large. Before this, a polycrystalline material, highest D33 people have obtained was 600, 650, at the most 700 if I stretch. This is almost double. So this is a quantum leap, I would say, from a value of 700 to suddenly 1500. Now, this is very interesting, published again 2 years ago by a group, China and Penn State. So this is a remarkable discovery. Now, I have just discussed about all these theories, the concepts. Here, what they say is when you put little bit of samarium into this PM and PT, it adds to the relaxer behavior of the system, and that's what they have explained. That it, and I've explained, when you add some relaxer behavior to the system, free energy becomes more and more flattened, so it's easy for the polarization to switch. That's what they say is the that was the argument they have put forth in this paper that gives rise to such anomalous behavior. And then we have also discovered something very interesting in another material, bismuth ferrite titanate lanthanum ferrite based material, a very, very large electrostrain of 1.2%. Now, as I showed before, this is a value which is almost what people have reported in single crystal of PM and PT, right? And we have got it in polycrystalline, which is and the best value before this was 0.7%, which I have mentioned for the sodium bismuth titanate base. So this is almost double the value of what people have reported. And there is a very interesting science behind all this. It's basically a non-MB system, basically. It's a tetragonal material which has a lot of disorder. So disorder in all these materials which I'm citing here are playing a very, very important role in improving the ferroelectric and the electromechanical, which is like the electrostrain which I'm showing here. So there's a kind of cooperative interaction between the disorder and the long-range polarization that cooks up to give you very large value of electrostrain and electromechanical property, including the D33. Another development is happening. This is away from the ceramic. These are being done by chemists, expert in making organic crystals. So here, this paper was in 2017, where they have shown that this peculiar, it's very, very difficult for me to even decipher, trimethylchloromethyl ammonium trichloromanganese. It's like reading a Sanskrit word. This single crystal of this particular material have shown D33, which is 185 picocoulomb per Newton. Of course, it does not come to the level of what the ceramics have shown, but this number itself is extremely large, because when you are thinking in terms of this organic material showing us. Now, organic material has the benefit because they have a density which is low as compared to the ceramic, because they are made of carbon, hydrogen, and some heavy element here and there, right? So the density is very, very low. So if you have such material, if you remember that one figure of merit I discussed about acoustic impedance matching, that if you have low density rho, then it is the material will be transmitting its wave very efficiently to the medium, right? So such materials can do wonders in making new devices, biomechanical applications, etc., etc. There is another interesting thing which is going on in parallelly and in the ferroelectric community is energy distribution. You have some lectures on energy storage and energy discharge supercapacitors. So, because ferroelectric materials have a natural spontaneous polarization, right? Now, what is so it has large polarization compared to a normal dielectric material. But so if you want to make use of this material to store energy and discharge energy, electrical energy, so the question of interest is this area under this curve. How much the area under this curve on this first graph which I'm showing, I'm trying to highlight. Perhaps you are able to see this. So the more the area under this curve, the more is the energy density you can store, right? And if the curve is linear, basically if you increase the field, it goes like this. If you decrease the field, it goes like this. So basically the whole energy is extractable. Means if you decrease the field, you can get the material discharge the whole material discharged completely, and you get entire energy as an output. So this is an ideal condition. Now, if you want to have this area large and discharge also large, so basically you want something like this. Now, ferroelectric materials have very large polarization by itself because it's spontaneous polarization. So it has an advantage. So the area can become large. The only difficulty in ferroelectric materials is that you cannot apply very high field. If you apply high field, there is a dielectric breakdown which happens because of this porosity, intrinsic porosity, and other things which doesn't allow high electric field to be applied. Secondly, if ferroelectric materials often also suffer hysteresis, which you have talked about, this is shown in the middle. So the energy which you can use after charging is only the shaded region, which is very small. So basically you want a very, very slim P loop, like in third case, and the material should be able to sustain very high electric fields so that you can go on increasing, so that the area under the curve becomes very large. So the entire emphasis on the ferroelectric material, there is a lot of material science at work here to design a material which can sustain very large electric field in a ferroelectric, so that you get very, very large energy storage, as well as because of the slimness of this loop, you also get most of the energy recovered. So this was published this year in Materials, where they could succeed to, of course, the multi-layered ceramics, some composition of sodium bismuth and so on. Not worry about this, but they got a very, very large value compared to what people have reported. So this is another fascinating area of research where a lot of material science has to be done to improve the breakdown strength of such material and exploit the large polarization for getting high energy storage and high discharge efficiency. Electrocaloric effect is something which I touched upon, just a glimpse of it, but this is a paper again published last year. I'm just highlighting that how ferroelectric materials are being used in wide ranging, continues to be relevant because of the different phenomena people are able to discover, which are very, very interesting, and also the new landmarks which are being established in the value of the piezoelectric coefficients. So this material is something ferroelectric material, and they claim to have very, very large electrocaloric effect near room temperature. It means that such material can cool about 3-4 degrees centigrade, very close to room temperature, by applying voltage. There are some other interesting features where we are trying to play the optical property of ferroelectric material by doping with some rare earth ion, applying electric field to change this the optical emission characteristic. I'll not go into the detail for sake of time. And also some of these ferroelectric materials are being used to change the color as a function of temperature. And so such materials can be used for optical thermometry, means non-contact mode of optical thermometry. This paper which published this year only, we are also working in this interesting thing. We have some new ideas here using the Raman part of this host and the photoluminescence part of the rare earth. We are clubbing these two things and designing material to get a large change in the color emission as a function of temperature. Just to add, before I have 1 or 2 minutes, apart from this perovskite-based piezoelectric, which are the conventional ones, ferroelectrics, there are also ferroelectrics which has been discovered in non-conventional material, which was useful in semiconductor industry like hafnia. HF42 is interesting for semiconductor industry. Such materials, when they're in the nanometer size, there's also show ferroelectric effect. The bulk doesn't show the ferroelectric. This is very peculiar. I think people are struggling to understand why nanometer size only gives this interesting PE loop, but when you make it bulk, this PE loop is vanishing. So this has a very, very different peculiar mechanism, and people are still struggling to understand how this ferroelectric appears in hafnium oxide thin films. And perhaps this is the last one. This is not a ferroelectric material, but a nitride, aluminum scandium nitride, which you cannot make, but you can always deposit in the form of a film onto some substrate. And you can do the compositional design such that the particular concentration of scandium in aluminum nitride gives a piezoelectric coefficient of about 25. Of course, it's not very large, but important thing is this is not a ferroelectric, but you can always grow on surface of any, make it as a coating and use that coating as a kind of piezoelectric sensor on some coating. So lot of interesting stuff. Okay, fine. This is the last slide. I think I am completing on time. So I have nothing much to say except for the fact that, so although piezoelectricity was discovered about 140 years ago, the field appears as exciting as a new branch of science, thanks to the new innovations in material science in terms of design of new materials, which gives very, very extraordinary properties, making them exciting, and advent of new functionality which has great technological significations. I think this keeps me busy in this area because of this exciting science and the opportunity as a material scientist to design material by understanding the fundamentals of what kind of strategy I should adopt to improve this or that property. So these are the fun things which we play around. And I thank you for your attention. This completes my talk.
Okay, thank you, sir.
Thank you very much, sir. Thank you very much for this informative talk. And you started from the basic and take us to the applications and explain very nicely why this ferroelectric materials has large piezoelectric materials. Not only that, you also cover that why these lesser ferroelectric materials have large value of this electrorestriction so that they can have a large value of piezoelectric materials.
Yes.
So you have addressed many important topics. So now this talk is open for the question. Participants who want to ask the question, please raise their hand. There is the option, Abhinav sir. Am I right?
Yes.
So they can raise.
Unmute them and then
There is raise your hand. And
so there are a few questions from the YouTube channel. For example, someone has asked that are these piezoelectric materials costly?
No costly, very cheap. Particularly the ceramics part is very cheap. If you want to have a single crystal, they are costly, but the ceramics are very cheap.
Okay. So there is another question by Mr. Vipin. He's saying that what will be the effect of D33 value if there is relaxer behavior during ferro to para electric phase transition? Will the D33 value enhance or will it decrease? Another question is related to layered perovskite. Why they don't have large D33 value? How can we improve that in layered perovskites?
The layered perovskites, I think the stubbornness of this structure, I would say, I'm using a loose term, stubbornness, in the sense that, see, why these perovskites are interesting, because they are quite flexible, open structure. You can put it different kind of elements and without the elements getting segregated out of the structure, they become part of the structure and they change the structure to the extent that it can change the direction of the polarization, causing interferoelectric instability, right? So, which we say is a morphotropic phase boundary. So the other structures, like in the layered structures, you don't have too much of that flexibility. If you put some element there, it will dissolve to some extent, but perhaps the structure doesn't change much. So the susceptibility of the structure to accommodate different kind of elements is limited in different kind of in the other structure. That I think that is one of the main reason which limits its high piezoelectric response, and that's why perovskite, which is more susceptible in the sense of accommodating large number of ions without throwing them out of their matrix, are interesting. it can make, because it can accommodate more number of ions, which even if it doesn't support ferroelectricity, but it will create disorder in the system, and a ferroelectric can be made to a relaxer ferroelectric, right? This a relaxer ferroelectric, once you make it relaxer, your Q value increases, the electrorestriction increases. So if you have a right combination of relaxer behavior, this is in response to the first question you just asked. If you have a right combination of the relaxer feature and also the long range polarization, a mix of this, right? That is the tuning of the composition. That is where you get much enhanced. You cannot have a all completely relaxer and there is no long range ferroelectric order. That also is not going to work. If you have complete long range order, well, it will have some piezoelectric effect, but lower. But if you have a right combination of this disorder and electricity, a long range ferroelectric order, on top of that, if your system is approaching a morphotropic phase boundary, then it's all nice. It's all nice. Then you have this cocktail of high Q value, high susceptibility because of the MP, high Q value because of the relaxer feature. If you have both this cocktail together, then you expect material to show very large piezoelectric response. I think I have answered both the questions.
Yeah, thank you, sir. So there is another question in the polycrystalline materials. So the question is, why doesn't these materials show piezoelectric properties?
Polycrystalline materials means ferroelectric polycrystalline material is piezoelectric. That's all I was talking about. That's right. Barium titanate, a polycrystalline barium titanate, if you apply strong enough electric field, if you pole it, that's what we call poling. That is application of very strong electric field, then you remove the field, the material is still polarized. And it is a piezoelectric material. That's what makes it cheaper, right?
Yeah, maybe the listener didn't pay attention, I guess. So there is another, that what is the importance of pyropiezoelectric effect in your study?
Pyropiezoelectric effect. Pyroelectric effect is the change of the polarization as a function of temperature. That is a phenomena which is used for making devices like infrared detector. I don't know. I don't get the question. Pyropiezoelectric effect, what he means. I think there is more need of clarification on the question.
Yeah, sir. We need more clarification, I think. And for previous question, it is already mentioned. You have discussed all the polycrystalline material which shows very good piezoelectric
Right.
coefficient.
That's what I said. Means the polycrystalline material showing a D33 of 1500. That was one of the recent discoveries, which is much better even in some of the single crystals. So it's all playing with the composition of this material. Perhaps he missed that part. Yes, any further question?
Anyone have the question, then they can raise their hand and you can ask directly from Professor Rajiv Ranjan. So you have the opportunity to ask the question directly. I think there is no question. So Abhinav sir, shall we close the session?
There is just one more question, that it is about antiperovskites. Do they show piezoelectric behavior?
I'm not aware of antiperovskite showing a piezoelectric behavior. I'm not aware of. I'm aware of antiperovskite materials in the context of this Heusler alloys or kind of thing, or no, this shape memory or magnetic shape memory alloys. But in the context of oxide perovskite, I am not aware of. I am not aware of.
Rajiv sir, I have one question.
Yes.
So, for example, if we have octahedral tilting, it is clockwise and anti-clockwise mixed.
Yes.
So, how easy is it to explore with the lab X-ray? Is it possible to evident that okay, this with the lab source X-ray, or we should go for high resolution measurement?
No, I mean, there are two things. If the tilt is sufficiently large, even the lab source, most of my work is based on lab XRD. I use the lab XRD for good quality lab XRD data reveals that. And otherwise, I go for neutron because neutron has a added advantage because X-ray is scattered by the electron, right? And oxygen has a Z value which is less compared to the other cations which is present. For example, in barium titanate, barium is a much heavier cation, higher Z value, large number of electron compared to oxygen. So the contribution of the oxygen towards the total scattered intensity is less. But so of course your superlattice peaks which you expect because of this toroidal tilt will have lesser intensity. Now, if the tilt is very small, the superlattice intensity may be very weak. And if you have not a good data with very good signal to noise ratio, perhaps it will be lost in the background. So if you do neutron scattering is not dependent upon the Z value. So oxygen scatters neutron as effectively as barium, was the cation. So the intensity of the superlattice peaks in neutron diffraction is always higher compared to in the X-ray diffraction case. But if you collect reasonably good data, means if optimize your conditions, with you can always you can get study these octahedral tilts, or you can understand what kind of tilt is there, in phase tilt or out of phase tilt, even with XRD data, lab XRD data. Most of my work, I will emphasize again, most of my work on the X-ray are not synchrotron based. Even I published my first PRL during my PhD in 2000 in strontium calcium titanate. It was just lab XRD data, Rigaku rotating anode was the source, and very good signal to noise ratio, and I could see the superlattice peak. Once you see the superlattice peaks, the rest is you have to index it. Once you know, if you index it correctly, you know whether it's an in-phase tilt or out-of-phase tilt. You can refer to that Glaz's paper, right? Or you can ask me if you want later on. If you see the peak, it's easy to know whether it's in-phase tilt or out-of-phase tilt once you index them. But if you don't see, then definitely you can't talk about it.
Thank you, sir.
So,
Abhinav sir, do you have any more questions?
Yeah, there are a few questions from, if sir can spare some time. So
Yes.
the question is regarding nanomaterials. For example, one question is that whether nanomaterials are expected to have better properties or not, and the other question is regarding graphene. That does graphene has such potential to show these kind of properties or not?
No, graphene is has conductivity, right? So a material which has conductivity, it cannot sustain electric field or polarization. So even if there is conducting materials are not interesting from that point of view when you are thinking of a device, because the polarization will, the conductivity will not allow you to apply apply electric field. Right? Only you apply electric field and sustain the electric field inside the material if you leave insulating material. So graphene, I don't think has any interesting feature as far as the piezoelectrical electromechanical properties are concerned. But there are some papers on molybdenum disulfide, I think I've read. Theoretically, people have expected that this one or two layer of molybdenum disulfide can show some ferroelectric features. But from the application point of view, I don't think they are interesting. What was the other question?
It was regarding the nanomaterials. Are nanomaterials tricky to determine?
Yes. So nanomaterials, it so happens that if you decrease the size to nano, decrease the size of ferroelectric grains to nano, then often the polarization is, you are unable to switch the polarization. It loses ferroelectricity. There is a tendency to lose ferroelectricity in the nanoscale, right? So there is always kind of there is a graph here for barium titanate. Here. For barium titanate, for example, as you are decreasing the size from 100 micron, you go to 1 micron, then the piezoelectric response increases significantly, but again it starts decreasing, which is not shown here, but it starts decreasing. So there is a peak grain size, average grain size, at which the property is enhanced. So at very, very small grain size, it is difficult for the grains, for the domain to switch. And so from the piezoelectric point of view, nanomaterials are not interesting. But as I said, there is one material, hafnia, which I was one of the last slide, I think. Yes, here. Hafnia. This shows ferroelectricity only in the nanoscale. But this is a different mechanism. People don't understand yet. People are still debating. But for this conventional perovskite or other materials, if you decrease the size, often this piezoelectricity or ferroelectricity is lost at very, very small sizes.
Okay. So maybe last question we can take if it is possible.
Sure.
The question is regarding the simulation. Can we simulate the D33 values before performing the experimental work?
You can simulate people are using first principle calculations to simulate D33. What you simulate is for the single crystal, of course. The people have simulated. There are papers. People are using a different kind of computational technique to simulate D33. They are, in the computational technique, they apply electric field also, and they measure the change in the polarization, and they calculate the dielectric constant, piezoelectric coefficient. People are doing it. If you just Google, you will find several papers. But what you get is ideal single crystal. Material science has no role to play there. As a material scientist, I am interested in playing with the size effect, for example, the composition effect, for example. Right? Those things are difficult to do in the computational technique. Or even if you do it, it's very, very costly. It's not manageable, at least in India, I guess. Yes.
I think we are done with the questions. So let's thank Dr. Ranjan for this very informative talk.
Thank you.
Thank you so much for accepting our invitation. We hope to see you in person sometime later, maybe.
Sure.
Thank you, Rajesh sir. Thank you very much for accepting this invitation. And really, as Abhinav sir said, that okay, we want to see you at IIT Jalandhar in person as soon as the things get normal. So once again, sir, we thank you from all faculty member and the organizing team from Department of Physics. Thank you very much.
Thank you.
Okay, sir. So now we will leave.
All right.
Okay. Thank you, everyone.
Thank you.
Abhinav sir. Sir, should I close the meeting now? Okay, thank you very much, everyone. We will meet at 3 o'clock. will be very much beneficial for you, and you will enjoy the whole event. So it is a great pleasure for us that Dr. Ranjit Ramadurai is among us. Dr. Ranjit is working as an associate professor at Indian Institute of Technology, Hyderabad. He is serving their Department of Material Science and Metallurgical Engineering. Before explaining about his talk and achievement, I would like to say that in the morning you have the talk about ferroelectric materials and ferromagnetic materials. So there are some interesting class of material where you can tune the ferroelectricity by magnetism and vice versa. So Dr. Ranjit is going to talk about such interesting material which is known as magnetoelectric materials, or the materials are also known as multiferric. So these two properties, so he will explain in detail about this. So Dr. Ranjit has completed his PhD from Indian Institute of Science, Bangalore in year 2007, and he worked as a postdoctoral fellow at CNRS Laboratory, Crismet, France. And he is recipient of various awards. I will read some of them. He is recipient of prestigious Alexander Humboldt Fellow in the year 2009 to 2012. He worked at Institute of Electronic Materials and Devices, Leibniz University of Hamburg, Germany. And he is recipient of MRSI Metal Materials Society of India Award, Young Material Researcher for the year 2016. He is recipient of DAE-BRNS Young Scientist Research Award in the year 2014. And he is also recipient of Excellence in Teaching Award in year 2013 in Indian Institute of Technology, Hyderabad. So, and he has handled many, and he is also handled and presently handling various research projects funded by different organization, for example, Department of Science and Technology, DRDO, Department of Atomic Energy, DMRL, and he has guided 5 PhD students and many master students. He has contributed more than 60 research articles in international journals. His area of research is multiferric, multifunctional thin film, piezoelectric sensor and actuators, magnetoelectric materials. So he has wide experience in this area. So we are fortunate that he is here. So thank you, sir, for accepting our request to be the part of this occasion. So now I will not delay much. So I invite you to deliver a talk on strain engineering in magnetoelectric multiferric and nanocomposite for magnetoelectric devices. Thank you, sir.
Thank you, Dr. Kiran. Very good afternoon to all of you. Dr. Kiran, I rely on you for feedback. I hope my audio is clear and my screen is also visible. If there is kindly intimate me, because I am just seeing my full slideshow screen. Okay, so just for beginning. Okay. Very good afternoon to all of you. Thank you, Dr. Kiran, for a very nice brief introduction. And today I will be talking about strain engineering in magnetoelectric multiferroics and nanocomposites for magnetoelectric devices. The outline of the talk goes. The outline of the talk is more or less distributed this way. So I will give a brief introduction about the magnetoelectrics, and then I will go on to ferroics. And I would also discuss a little bit about magnetoelectric multiferroics, and then the talk will focus on strain engineering in magnetoelectric multiferroics and what strain engineering is and what it is capable of doing in both individual systems like bismuth ferrite and ME composites. That is what I will be focusing for today's lecture. Okay. And finally, we'll go with the summary and conclusions part. Okay. So let me start. I heard that Kiran was saying a lot of master students and as well as it's a mixture of population. That is what Dr. Kiran told me. So sorry for the faculty who are in the audience. So the first few slides can be very elementary, and it is there for the sake of the students. Okay. So for the students, I would like to ask you a question like, what if, I understand you don't have to answer. I'm just posing the question and I will answer it myself. So you don't have to worry. What if atoms act like point charges? Okay, so we all have studied about point charges in our elementary school sciences. Okay, so when I say a point charge, we all know the charges can be either positive or negative. And when we have a point charge, we also know there is if it is two-dimensional, it is a circularly symmetric field around it. And if it is three-dimensional, we know that there is a spherically symmetric electrostatic field around a point charge. This is something, a basic school physics that we have studied. And this charge can be either plus or minus, because electrically we can have a monopole that is possible to be isolated. Okay, so let's assume that it can be either plus or minus in this case. But the interesting thing comes when this charge starts moving. And this charge can start moving either in a conductor or in free space. So when the charge starts moving, we also know from our school physics that it starts creating a small magnetic field around the current carrying conductor. So basically an electric charge, when it is static, so it is simply like a spherical ball which is radiating some electric potential around it. But when it starts moving, it kind of creates a induced magnetic field around it. That is what we have studied in our class 12. So basically, when we have a change in electric field, that means it is kind of inducing a magnetic field. And vice versa is also possible, and that is what we have studied in our basic physics. So when you have a change in magnetic field, you will be able to induce an electric field around it. So that is what conventionally we have studied in our basic sciences as electromagnetic induction. So one can induce the other and vice versa. That is what we have studied in the simple physics concept. Okay, but now the story becomes very interesting when you have an electric dipole, and if it is starting to oscillate around a given position, and that also we have studied. We know what interesting thing that kind of a dipolar oscillation can give rise to. So basically, we know when a charge is static, what will it do? And we know when it is dynamic, what it can create. And when they couple with each other, if it is an electric dipole and if you have a magnetic field around it, and if they start varying in both space and time, then you know there is something interesting that can happen, which is we know it as an electromagnetic wave generation from the oscillation of dipoles, electric dipoles. This is something which we know from our class 12. But now the interesting question that people were asking is whether this kind of induction of one from the other. So basically I can have a dipole. Can I induce a field of magnet? And can I have a magnetic dipole or a spin? And can I induce an electric field inside the material? So that is these things can happen even in free space. So there is no condition of material. But once it comes to material, it is a very interesting question. What will happen inside a solid? When we are, of course, this is more of an energy materials workshop, so we will focus on the material aspect of it. So we will not talk about the individual charge and dipolar oscillations in free space or something. We will always talk about this inside a solid. So what happens inside a solid is a very interesting question. It's not that we have asked this question first. There are several people who have asked this question earlier, and they have also come up with an answer. But now we can actually categorize these materials based on electrically characterization as well as magnetic characterization. So conventionally, we kind of separated out these two materials, electrical property like which are insulating, as well as some materials which can be electrical property of materials and magnetic property of materials. So this is our conventional understanding about materials. So when I have an electrical charge or a charge inside a compound, of course we can have charge in various forms. We all know that. But the moment I apply an electric field, what will this charge inside that material will do? Of course, every charge responds to the applied field. So what we are going to characterize is the way the material is responding to the applied electric field, and that is what we do as an electrical characterization. If I have a metal and I apply a electric field across if I apply a potential across the metal, then the charge inside is having a capability of transferring energy by moving inside. But that kind of a luxury is not present in all materials, and that is what we call it as electrical conduction. And we know that there is excess free charge present in the material, and that free electrons are responsible for conduction. But now, if we have an insulating material where the charge is very tightly bound, it is not a loosely bound system. I have a charge that is tightly bound to an atom, and that is not permitted to take part in conduction process. Now interesting thing happens, but the charge will always respond to the external disturbance. So the way the charge responds to the external disturbance inside the solid is what is categorizing different kind of materials that are present and different kind of phenomena that is present inside a material. Okay. Now if I take a single atom, we all know that we have nucleus and then there is an electron cloud. The moment I apply an electric field, the negatively charged electron cloud will respond in a way that is opposite to the positively charged nucleus. So if you assume something like this kind of center of mass kind of concept, and then assume that there is a center of mass kind of center of charge for the plus, and assume there is a center of charge kind of concept for all the negatively charged cloud, when there is no applied electric field, both the plus and minus coincides on the same point, like a center of mass kind of an imagination. But the moment I apply an electric field, because they respond in the opposite direction based on the field direction, the center of charge point for the positive and the negative kind of response displaces in the opposite direction. This gives rise to something called as a dipole moment inside a material. And what are all the sources of point charges in material? If such a scenario is present, if it is a metal, we know that the electron will simply move and then you end up in conductivity. Now I am talking about a material that is non-conductive. That means a charge is very tightly bound to the nucleus of that particular species which it is made of, but it has to respond to the applied electric field. And how will it respond? It can respond in variety of different ways based on what that solid is made of. We all know every solid is made of atoms and nucleus is present. So we all know that there is a electron core around the nucleus, which means the electron cloud surrounding the nucleus is going to always respond to the applied electric field irrespective of what material that you are dealing with. If you are dealing with a metal, the free electron is dominating the property, so you will not be able to capture this phenomena that is happening inside. But if you are dealing with the insulator, that means the electron cloud around the nucleus, which I call as ion core or core electrons, will obviously respond to the applied electric field, and this kind of displacement of charge centers is called as polarization in a given material. The polarization in a material can come from different number of sources. One of the sources is this particular electronic polarization, which is a universal phenomenon. That means all the atoms that we are dealing with, except for hydrogen, is going to have some core electron into it, and then all the other atoms, when you apply an electric field, the core electrons as well as the electron cloud around them is supposed to respond to the applied disturbance. Of course, the other common thing is you can always have an ionic solid, which is having a cation and anion kind of a configuration, and where the net charge center is always coinciding at like a center of mass. But the moment I apply an electric field, the net charge displacement is possible. That we call it as an ionic displacement kind of a polarization. But sometimes you can also have a structurally non-symmetric system, like a molecule, like a water molecule. It is a most common example. You can have a molecule which is having a particular dipole moment which is uncompensated. In this diagram, I hope you can see the pointer moving around. So in this diagram, in the water molecule, you will have a net dipole moment always associated with it. So this molecule as a whole rotates and responds to the applied electric field. Okay, this kind of polarization is called as orientational polarization. So what we have inside a solid which is having a point charge. So basically, I am kind of eliminating the metals in the discussion. because we know that the metals immediately transfer the energy in the form of conduction. So that means the electronic charges that are present responds in a very unique way. But when you come to non-metals or insulating systems, so you can have variety of charge sources that are present inside the material, like the electron cloud around the nucleus, the ionic displacement with the solid, and the net dipole moment from polar molecules, and also something called as space charge polarization, that is kind of an extrinsic to the system. We will not discuss that part detail here. So there can be various sources of dipole moment possible. So if you understand, inherently I have eliminated metals. If I have eliminated metals from the basic school chemistry, we know that insulating materials are covalently bonded solids. If you have heterogeneously valent covalent solids, you are expected to have some electronegativity difference. And the bonding takes care of the completely filled configuration for the individual species. That is the reason we know that they behave like insulators. So basically materials which are having completely filled electronic configuration will have a completely filled valence band, and then there is a band gap. So when I apply an electric field, they don't take part in the electrical conduction, but they respond to the applied electric field in a very different fashion. We call it as polarization. This is conventionally we would have studied in our school books called as dielectrics. But then comes the interesting counterpart. As the title says, this is called as the polarization of the given material. But now the interesting counterpart is the magnetism. We have studied these things as magnetic materials. Okay, we have variety of classifications, and then in this ferromagnetic you can have an ocean of different interesting phenomena that is happening. That is not a topic of our interest, so I will not go into that. But what we know is there is a classification of a magnetic and non-magnetic material. Okay, and we all know what are all the sources of magnetic moment in a given material. From the earlier slide, it was very evident the moment you start making a charge to move in a circular loop, we thought we could see that we are able to generate a magnetic field. So basically, there can be a variety of sources for magnetic moments that is generated inside a solid. Some of them are the spin moment of electrons, we all know that, and then the orbital momentum from the nucleus, and then the change in orbital angular momentum due to the magnetic field that is applied externally. So these are the various sources of magnetic moments. So fundamentally, there is a difference between these two properties. The spin moment cannot be completely paired. You cannot have compensated spins. So if you have a completely filled configuration, you are more likely to have a compensatory spin arrangement. What does it mean? A magnetic dipole moment from upward spin as well as a magnetic dipole moment from a downward spin, they cancel each other, and then you end up with a zero magnetic moment in the sample. So that means you define those kind of materials as non-magnetic material. Your insulators that we discussed just now are kind of similar to this material which have a completely filled configuration. So you don't want an unpaired electron in the left side of my material to have this kind of a dipole moment or polarization phenomena. But on the contrary, on the right side, you want an electron to be unpaired. So you want an electron to stay alone and respond to the applied magnetic field. So effectively, you will measure a magnetic moment in those materials. Okay. So from the fundamental understanding of these properties, so one demands a presence of unpaired electron and the other demands a presence of completely filled configuration. So they were kind of contradicting each other. So that is the point which I want to make from this slide. So this is something that we have as a conventional understanding. But then because of this kind of understanding in terms of origin, people have always dealt with them separately. If you look at my first point, the electric and magnetic ordering in solids are always considered separately, because the electric ions, electric charge of electrons and ions are responsible for charge effects, and the electron spin governs the magnetic properties. Okay. So, however, finding a connection between the spin and the dipole moment of a lattice, or whichever is the polarization that is present in the material, which was very inquisitive for various scientists, and of course it dates back to Pierre Curie, who has kind of indicated a possibility of electromagnetic kind of induction possible inside a solid. And then later Landau and Lipitz also mentioned that there is possibility of linear coupling between the electric as well as magnetic ordering that is present inside the system, or the electric and magnetic fields present inside a medium. However, they also make a note in 1960, close to end of 1959, till present, no such observation is made in any substance. So that is the comment that they make, and then the field is almost left there as an open question. Okay. So the idea of electric dipole moment or the electric field and the magnetic field coupling inside a medium was left as an open question. And that equation is very simply here. So you can simply think of this as the thermodynamic free energy based on the polarization as well as its function of electric field. So you can think of it like the change in free energy with respect to electric field. You will have, of course, something called as polarization, that is in the absence of an electric field. We will soon come to that. And then the polarization in the presence of an electric field. And then you also have a term that couples between the polarization in the presence of magnetic field. Okay. So by equation, we could see that this is a polarization and it is connected with a magnetic field by a coefficient called magnetoelectric coefficient. And similarly, then the magnetization, which is actually which is generally a function of magnetic field, is what is written in the thermodynamic free energy. But you could always see there is a higher order term that couples with the electric field also. Okay, these two terms by symmetry are the same. That means you can apply a electric field and measure magnetic moment, and you can apply a magnetic field and measure the polarization, which is nothing but the dipole moment for unit volume. So they both are equally magnetoelectric coefficients, and by magnitude, due to symmetry, they are expected to have the same value. Okay, so this was identified experimentally in chromium oxide, but the only problem is it was identified at very low temperatures and the magnitude of this alpha was very low. So practically it was considered as, even though if the effect of interaction between an electric and magnetic field is present in the medium, but it cannot be of any practical use. So that is the kind of understanding the earlier experiments indicated. Point number one, the effect was at very low temperature. And point number two, the effect was very minimal, so we will not be able to use it for any application. So that is the kind of a conclusion back then. The real twist comes especially based on the first terms. If you look at the first terms, they are all spontaneous terms. What does it mean, spontaneous? That means I prepare a material, then I don't subject it to an electric field or a magnetic field, but the magnetic moment or the dipole moment inside the material is kind of giving rise to a polarization, giving rise to a magnetization. That means without an external stimuli, these systems or dipoles are kind of arranged themselves or ordered. That is what people call it as ordered systems. So if you have an electric dipole moment that are ordered in a lattice or in a solid without an applied electric field, you call it as a spontaneous electrically ordered system. And if you have a magnetic moment that is ordered inside a medium, you call it as a spontaneous magnetically ordered system. Okay, so the twist in the problem actually comes when you talk about spontaneously ordered systems. What are spontaneously ordered systems? I'm sure this morning you heard a very nice lecture on ferroelectric systems, which is Dr. Kiran also said you had listened to magnetic materials as well earlier. Okay, so here I'm going to indicate two spontaneously ordered systems, one with an electrical ordering and with the magnetic ordering. So the schematic shows I have dipoles present inside my material, and the dipoles can come from any of the origins that I showed you earlier. It can be an ionic displacement, or it can be a orientational dipole moment, or it can be a natural inherent electronic polarization also. However, that polarization is very weak. So naturally, on most of the spontaneously ordered systems, you will have either ionic displacement or orientational polarization. That is what will give rise to a strong dipole moment in the system. So I'm talking about a system which is having a spontaneously electrical ordered system, and then it can another system which can have a spontaneous magnetic ordering present inside. So basically, these two are again separate class. one needs a high amount of unpaired electrons. The condition or the requirement of having the magnetic moment or magnetic ordering, or the condition or requirement to have an electrical dipole ordering has not changed. It is still the same. Fundamentally, you need to have an insulator here and you need to have a half-filled configuration here or partially filled band here. So the requirement is still the same, but however, when you have a spontaneously ordered system, the interaction between the electric field and magnetic field, or the polarization and magnetization, is expected to be enhanced. And that is what the interesting thing comes into picture. Since you have heard a lecture on ferroelectricity, I will just tell you, ferroelectric phenomena is ferroelectricity is an example of spontaneously electrically ordered systems where you have a hysteresis loop, which is a fingerprint of any ferroelectric material, and you can have the polarization at zero field, which I call it as a spontaneous polarization that is present in the material. Since in the morning you had a very detailed lecture, I'm not going to detail these things here. So I'm going to tell you that just a spontaneously electrically ordered system will exhibit a phenomena called as a ferroelectric behavior, and it has two thermodynamically stable state, which is forming the basis of your memory device application, where you can have spontaneous polarization, which are two equally energetically favorable states. So that means you can have polarization, spontaneous polarization here plus P and then minus PS actually. Both are thermodynamically equal energy states. That is what this diagram states. Okay. Now, of course, yes, there is something called as a domain theory, which will explain this ferroelectric behavior, and domains are considered as the region which has a uniform polarization. So the domain theory of ferroelectricity is borrowed from ferromagnetism, and the phenomena itself is a borrowed theory phenomena. That is why the word ferro is still there, even though this word ferro has nothing to do with iron based elements that are present inside the compound. Since the theory is borrowed from ferromagnetism, the word ferro is always attached with the electric counterpart as well. Okay, so that we all know how this hysteresis behaves and the domains, how they respond to the applied electric field. So at point number C, all the dipoles align in the field direction, and then at point number E, exactly opposite field, equal and opposite field. So all the domains are aligned in the opposite to that of the C axis. Okay, so this is something that we know in the ferroelectric materials. So now, some of the crystal structure, some of the material aspects or the crystal structure aspects is the essential condition for a material to have ferroelectricity is non-centrosymmetry. And this morning I see that he had made a very nice chart of what are centrosymmetry and non-centrosymmetry point groups. So I will not enter into those kind of details. So you can have an AbO3 perovskite kind of a system exhibiting ferroelectric behavior, and these materials are the simplest among the materials that are exhibiting ferroelectric kind of a behavior. Some examples are barium titanate, lead titanate kind of material. And when you have this AbO3 kind of structure, there is a BO6 octahedra that is formed inside the unit cell, and the B cation, which is present at the middle of the unit cell, can rattle, which is permitted to rattle based on its ionic sizes, and that rattling give rise to this spontaneous polarization, and that is what is schematically represented here as two equivalent positions of the rattled B cation, and that is actually represented here from the thermodynamic double well potential schematic. Okay. Now, what is it non-centrosymmetry, or what is it centrosymmetry is called? So I am sure most of you would know about it. I am just brushing upon it. So if I have a system which has for all x, y, z, if there is an equivalent minus x minus y minus z, then I call this as center of inversion. That means the system is possessing centrosymmetry. But now if I have an ionic displacement that is present inside my plane, let's say here I am showing the plane of the octahedra. So if the ion is displaced in the plane of the octahedra, so it will give rise to some kind of a permanent dipole moment that is associated with this arrangement. And that is called as a non-centrosymmetry. That means in this kind of an arrangement, for all x, y and z, you will not have an equivalent minus x minus y minus z. So that breaks the inversion symmetry of the material or of the unit cell, and that is where the ferroelectric origin comes into picture. So non-centrosymmetry is one of the essential criteria to realize ferroelectricity in any given material. Of course, I am taking a detour for the titanates, and this is something people know just for the students' sake. So most of the titanates are non-ferroelectric in this particular category, but only when you reach barium, you kind of achieve ferroelectricity. The reason, there has been two theories proposed by both the surname of Cohen. One is called as senior Cohen and the other is called as junior Cohen. This first one explained it based on electrostatics. So if you look at it, the magnesium to barium, the ionic radius of magnesium to barium continuously increases until you reach barium. As the ionic radius increases, the A cation ionic radius increases, the interaction with the oxygen is becoming more and more strong. So the interaction between the BO6 octahedra, B cation and the oxygen anion is weakened. That means the B cation is permitted to rattle. So the B cation is permitted to rattle because the larger size of A cation is attracting all the oxygen and it is kind of weakening the bond between the B and the O system that is present. That is based on the electrostatics. Even later, when first principle studies and the electronic hybridization was discussed in the quantum mechanical picture, it was known that the A cation kind of weakens the hybridization between the titanium and oxygen in this case, if you have a titanate kind of a system. So basically, the A cation is equally responsible, but the permanent dipole moment that is coming to the system is coming into the unit cell is coming from the rattling of the B cation or the displacement of the B cation that is present in the unit cell. So I will give a break here for electricity. I'm not going into details of ferromagnetism. Okay, these class of materials, one is ferroelectricity, the other is ferromagnetism. You can also have something called as ferroelasticity. Okay, it is basically a material that can possess spontaneous strain in itself. Okay, so it will possess a hysteresis loop as a stress strain curve, and then if you have a magnetization and the magnetic field, you can have a hysteresis loop, and then you can have a polarization and electric field, you will have a hysteresis loop. So basically, you have a system that is electrically ordered, a system that is magnetically ordered, and you can also have certain materials that can have spontaneous strain present inside. So these class of materials, which are called as spontaneously ordered systems, form the term called ferroids. Now again, the word ferro comes because of the ferromagnetism. Okay? These properties are also called as the polarization, the magnetization, and the strain involved in the system. They are also called as thermodynamic equilibrium properties. We know that because when you kind of multiply them with the canonical conjugate, you get the free energy of them with a proportionality constant. So that is what we all have studied in the Gibbs free energy expansion. You can have polarization electric field, you can have magnetization magnetic field, you can have stress and strain, and then you can also have cross coupling. The whole talk today is about cross coupling between polarization and magnetization, but however, how to use the third one to alter the interaction between these two. So that is why the topic is kept as strain engineering of electric and magnetically ordered systems. Okay. In terms, I'm going to talk about systems that possess more than one ferroic ordering. Okay. So what I have established now is there can be materials that can possess electrical ordering, and there can be materials that can possess magnetic ordering, and there can also be materials that possess spontaneous strain in them. But now we are going to talk about materials that can possess more than one ordering simultaneously, and that is what we're going to discuss now. So I have already discussed about what is ferroelectricity, what is ferromagnetic, and what is ferroelastic. At least to a small glimpse, I have touched upon ferroelastic, if not in detail. Okay. So now we are going to talk about materials that can have more than one order parameter or ordering in the system. When I say ordering, it is either electric or magnetic. And as I said, today most of my discussion is going to be based on electric and magnetic ordering. But however, I am going to use the third equilibrium property to control the other two equilibrium properties. So here you see a Nye pyramid, which is very famous Nye pyramid from the textbook of Physical Properties of Crystals by J.F. Nye. So probably some of you might have read that textbook. So here what you have is a ferroelectric behavior where polarization and electric field. Some people call this as displacement current, and some people call this as polarization. Anyway, both indicates finally they indicate the same. Okay, so electric field and polarization, the magnetic field and magnetization, stress and strain. These are coupled properties. We know that these are thermodynamically canonically conjugate properties. Okay, but now we are going to talk about interaction between the other order parameters. We all know that if I stress, then the relation with polarization is piezoelectricity. If you apply an electric field and then if you are able to strain the system, today morning you have listened that it is called as inverse piezoelectric effect. Okay, but now we are not going to focus on this side because today morning you had an interesting discussion about the left side of this pyramid. Electricity, polarization, stress, strain, and their intercoupling is what you had discussed this morning. But today what we are going to do is magnetic field polarization and electric field and magnetization is what we are going to discuss today. Okay, so I will get back to the discussion. So if I have material that can have simultaneous existence of more than one order parameter, then we can call them as multiferroic system. The term multiferroic was coined by Schmidt. Okay, so what is magnetoelectric effect, and what is if I can have a system which can have spontaneous ordering and magnetic ordering, but without intercoupling also, it is quite possible. What do I mean by that? I have polarization. I look at this equation. I have polarization, and then I have some constant related to electric field, and then the cross coupling comes here. Alpha ij and h. Probably I can make a material with solid solution that can one ion that is present can give rise to magnetic moment and another ion that can give rise to this polarization effect. In that case, there are certain materials that may not have a very strong interaction also. I may also end up in a material that will give a very weak interrelation between polarization and the magnetic field. So a magnetoelectric effect is defined as the polarization induced in a material based on magnetic field or a magnetization induced in a material based on the applied electric field. As I said, based on symmetry, they both carry the same sign and the magnitude. Okay? So this is called as magnetoelectric effect. Now the question comes. Let's get back to again the origin of behavior of this material. So this is a nice Venn diagram. So if the thin black line is talking about materials that can have some kind of an induced magnetic moment because of applied magnetic field. Okay, I call them as magnetically polarizable material. And you can also have our normal conventional dielectric materials which can get polarized under electric field. Okay, inside the subset of magnetically polarizable and electrically polarizable, you have spontaneous ordered system. The thick line of green shows the spontaneous electrically ordered system, and the thick line of black shows the spontaneously magnetically ordered system. And the overlapped region talks about the multiferroic region, that is coexistence of magnetic as well as electric. But what is the interest today is not a mere presence of only magnetic ordering and electric ordering, and they both have to interact with each other, and we should be able to have a change in polarization because of magnetic field and a change in magnetization because of an electric field. So our interest is basically a magnetoelectric coupling which is present inside a multiferroid. So then it is a useful material. Okay, fine. But the hunt for that is magnetoelectric is a central spot for material researchers. So what does it mean? I don't want only a multiferroid material. It can have magnetization as well as which can exhibit a magnetic hysteresis and which can exhibit a polarization hysteresis. That is not the only interest here. So you should have these two simultaneous ordering and they should also interact with each other. There should be a coupling between the polarization and the magnetization. Okay, but the naturally existing room temperature multiferroics are very, very rare. Okay, so our focus is really on the magnetoelectric multiferroics. But now one can ask a question, why are they very scarce? They are naturally very scarce. That means the thermodynamic are they thermodynamically permitted to have such a characteristics. So that comes as the next question. Why is this phenomenon naturally very scarce? If you remember, I said electricity and magnetism are dealt as two separate columns in the solids. Okay, but here what we are going to talk about is why did we treat them separately? If you remember, all magnetically ordered system, I said it should have a partially filled configuration, which means a DN configuration. Okay, and on the contrary, when you are talking about a ferroelectric material, you should have completely filled configuration. This is a very contradictory demand for a property to exist in a given material. This is a very contradictory kind of a demand for the existence, and that is what makes the phenomena very scarce in nature. So to have a spontaneously dipole ordered, you should have a completely filled configuration, and to have magnetically ordered, you should have a partially filled configuration. This makes that phenomena to be very scarce. But it is scarce, but not null. That means there may be very few materials that exhibit, but it is not that there are no materials at all that they exhibit this behavior. Okay. So now we are going to talk about some materials which can have this magnetoelectric multiferroic kind of a behavior, and there is a kind of an interesting classification made by a very nice physicist Daniel Chomsky on the Physics 2 2009. It's a very famous summary of multiferroic material. So if somebody is interested in multiferroic, so you should recommend this particular article, which is free again. Okay, so this classification of multiferroics was made by Chomsky, and what does it say? It says type 1 and type 2. Okay, so he is basically classifying it based on who is responsible for the polarization. If you remember, I said there are the magnetic ordering and the electric ordering is dealt separately. But now, if I have a material like the type 1, where you know there are most of them are perovskites, so you can have a cation and then you can have B cations. Okay, let's assume there is a system where the A cation is giving rise to some kind of distortion in the structure that will give rise to dipole moment in the material. However, the B cation is still a partially filled configuration, but it can have an uncompensated magnetic moment in the system. That means the electrical ordering or the dipole moment comes from one particular ion that is present, one particular sublattice that is present in the crystal structure, and the magnetic contribution can come from another particular sublattice that is present in the crystal structure. This is one class of material, and he classifies them as type 1. That means the origin of ferroelectric or the dipole moment comes from one particular cation, and the origin of magnetic moment comes from another type of cation, which means the coupling between them is not necessarily to be very strong. And of course, these spontaneously ordered system loses their ordering when I heat them. And the temperature where the electric ordering disappears, I call it as Curie temperature. And if I have a ferromagnetically ordered system, I call it again as a Curie temperature. But if it is an antiferromagnetically ordered system, the temperature where the ordering loses, I call it as a Néel temperature. Okay. But in these materials, which are type 1, you can have a different origin for electric ordering and a different origin for magnetic ordering. So they can have a weak coupling and the effect can disappear at different temperatures. So that kind of materials is what is called as type 1. So you can have a TC, electrical TC separately, and you can have a magnetic TC separately. Okay. So if you can have these kind of materials, I classify them as type 1. Type 1 kind of materials. And you can also have type 2 kind of classification. I will come to that shortly. I will not discuss in detail about type 2, but these type 2 materials are known to have very unique magnetic ordering, and these materials, the magnetic ordering is such a way that that gives rise to a dipole moment in a very particular given crystallographic axis. Here, the polarization is originating from the ordering that is present, from the nature of magnetic ordering that is present, which means the temperature at which the magnetic ordering disappears, the polarization also disappears. So here, the magnetic ordering is the one that gives rise to polarization, which means the coupling between the polarization and the magnetic ordering is very strong in this system. But the only drawback is this kind of coupling is at very low temperatures. You can have a lot of magnetic ferroelectrics, which kind of the magnetic ordering kind of breaks the inversion symmetry and gives rise to polarization. But those materials are considered to be strongly magnetoelectrically coupled, but however, these magnetic ordering are at very low temperatures. Fine. So now we are going to talk about one such, this is one example of such material, which is called as type 2 multiferrite. It is called as terbium manganate, which is very famous magnetic ferroelectric. Okay. At 27 K, there is a magnetic ordering that induces the polarization. That is what is presented here. Okay, fine. But our interest is more on the type 1 multiferroics because of a different reason. Okay. When I come to type 1 multiferroic, I want you to focus on one particular system, which is bismuth-based multiferroics. This bismuth is a cation that is present, and that has 6s2 lone pair that is in its configuration, and this 6s2 lone pair is kind of inducing a structural distortion in the unit cell because of its stereochemical activity, and that is giving rise to a dipole moment or a structural distortion in the unit cell itself. And that is the origin of ferroelectricity. That is why iron 3+, even though if it is not a completely D0 configuration, but it is able to, this compound is able to exhibit ferroelectric dipole moment in spite of having non-D0 configuration, because the bismuth there is able to induce a dipole moment in the lattice. So this kind of materials have a different TC and TN or TC based on magnetic order. Okay, so I think I have established certain things. So now we can really talk about what strain can do in these materials to tune their structure and property. That is what we are going to deal today. Okay, so as a quick recap, what I have told you is you can have electric and magnetic ordering that is present in the system, but their interaction between them is very weak. But the moment when you have spontaneous ordering, there is a possibility for interaction, but however, those interactions are weak in certain systems and strong in certain systems. So when I say there are certain systems are strong, there are other drawbacks like type 2 multiferroics where the effect is at very low temperatures. Okay, but now when I talk about type 1 multiferroics, or in other words, so far whatever room temperature multiferroic that we know, that bismuth ferrite is the only compound that exhibits a room temperature multiferroic. So I will spend another 10 to 15 minutes in bismuth ferrite, and then I will go on up to the Me composites. I think I have time up to 4:30 if I am not wrong. Okay, fine. Yeah. So we will talk about bismuth ferrite.
Yes, you have time for 30.
Fantastic, thank you. So we can spend some time on bismuth ferrite and the Me composite. Okay. So now let's talk about this compound bismuth ferrite. So as I said, it is a type 1 multiferroic. Sir, why do I call it type 1? Look at this. The Néel temperature is at 643 Kelvin and the transition ferroelectric Curie temperature is at 1105 Kelvin. So that means one type of ordering is not essential to have the other type of ordering. The origin of this ordering is coming from different sources. That is what it means when I call it as type 1 multiferroic. And bismuth ferrite is a very simple perovskite exhibiting room temperature multiferroicity. The only naturally existing compound that exhibits room temperature multiferroicity so far is bismuth ferrite. Okay, and it has in the bulk it has rhombohedral structure. When you have a cubic construction, it will give rise to like 3.8 or 3.9 kind of angstrom. Okay, and what kind of magnetic ordering it possesses? It possesses a complex cycloidal spin ordering, which is giving rise to a canted antiferromagnet kind of ordering, and temperature at which it loses is 643 Kelvin. Okay, but at room temperature it is still ferroelectric, and the ferroelectric transition is a very high temperature, which is like 1100 plus Kelvin. Okay, so bismuth ferrite is a very ideal system because it exhibits multiferroicity at room temperature. It is easy for studies in various other forms because both the magnetic transition as well as the electric transition is at relatively larger temperatures. Okay, so now some of the characteristics of this. Okay. So the polarization value The polarization, because of the B 6s2 lone pair that you have in the bismuth, the 6s2 lone pair is expected to distort the B cation along the 111 axis. So the polarization axis is along the 111 direction, and then by default you can assume that because of the rhomboidal structure, by default we know that the polarization is going to be along the 111 axis, and it has a very large polarization along the 111 axis, close to 100 microcoulombs per centimeter square. Okay, so bismuth ferrite is also known as the largest polarization exhibiting room temperature ferroelectric material so far. Okay. And what kind of magnetic ordering it has? It has a G-type antiferromagnetic ordering of Fe3+. And magnetic ordering, as I said, it has a complex cycloidal kind of ordering. So what does it mean, cycloidal kind of ordering? So if I move from one unit cell to another 64 unit cells, you can see that the spin moment of iron is kind of taking a turn of cycloid and then completing a wave pattern. And the periodicity of that spin arrangement is 64 nanometer. It is also known as an incommensurate cycloidal ordered system. That means if I make it as a nanoparticle less than 60 nanometer, the cycloid will not compensate the spin completely. So you can expect a weak moment present from the nanoparticles. Okay, that means it is not a completely compensated system. That is why we call it as incommensurate system. So it does not change with the size of the system that you are studying. So if you take a nanoparticle of bismuth ferrite which is of 10 nanometer size, if you can make that as a spherical particle, that means you will not see antiferromagnetic characteristics. You may also see a weak ferromagnetic behavior. That is what it means when I say incommensurate cycloid structure with a periodicity of 60 to 64 nanometer. Okay, so these are the characteristics of bismuth ferrite. That is what makes it very interesting. Okay, this I already explained. So the room temperature multiferrite with a simple perovskite. These are the lattice parameters and these are the characteristics. Now we have more interest on the thin films and devices group. So now I will go stepping slowly into the work that we are doing. Okay, so we will go on to the kind of the research activity that we do in bismuth ferrite. Okay. So what we do is we do something called as an epitaxial growth of thin films. So we have a pulse laser ablation and we try to take a single crystalline oxide substrate and then we try to deposit these materials in the form of thin film, and we call it epitaxial growth because the substrate that we have, which is strontium titanate, and the layer that we grow, which is bismuth ferrite, are crystallographically related. So what does it mean? When I take a strontium titanate single crystal, which is 001 oriented, I will have a bismuth ferrite film, which is also 001 oriented. The film will take orientation of the substrate. But that is not what is epitaxy. Okay? In general, epitaxy means the film and the substrate will have crystallographic relation. That's all. The crystallographic relation can be material dependent and substrate dependent. What do I mean by that? Probably, if I grow bismuth ferrite in any other single crystal, like a neodymium gallate or dysprosium scandate kind of subsystems, then probably the 001 orientation will grow along the 110 of the single crystal substrate. So, epitaxy means the film and my substrate has a crystallographic relation. What relation it possesses with the film and the substrate, one has to specify explicitly after testing. Okay, or you can also choose it based on the lattice parameters. So if you take a cubic construction of bismuth ferrite, the planar lattice parameter is around 3.9 angstroms. The strontium titanate lattice parameter, which is known to be a perfect cubic system, is around 3.9 angstroms. So since I have a very close lattice matched behavior, I can choose that as a substrate and to grow a film of given unit cells dimension on this substrate. What you see on the right side is a transmission TM image of bismuth ferrite grown on STO substrate with a very nice lattice coherency that is present. Okay, fine. That is not the whole story. Okay, so bismuth ferrite has been extensively studied because of its room temperature multiferrite characteristics. Okay, but our interest is mainly strain engineering. We'll soon come to that. Before that, I want to establish the fundamental science behind bismuth ferrite in a much more deeper fashion. Okay, so basically, if you remember, I said the polarization along the 111 axis. there's a rhombohedral structure. So obviously triple one becomes the easy axis of polarization. So that means the polarization is along the triple one axis. If I have triple one axis as polarization, I can have 8 equivalent directions as polarization. Okay, so if some of you might remember that, so when I have 1 1 1 axis as polarization, I can also have 1 bar 1 bar 1. I can also have 1 bar 1 1 bar 1 bar. So I have 6 plus 2, 8 equivalent axes. Okay, so now that is what is presented here. So in Bismuth ferrite, you can have triple one direction as the easy axis of polarization. If I have triple one as the easy axis of polarization, I can also have 8 equivalent direction. Other way of imagining is this: you can have a unit cell, and then you can have 4 polar axes on the top half, and then the 4 polar axes on the bottom half. You can also have it that way. So you can think of that as it equivalent polarization axes that are present in the unit cell. Now you can imagine that the polarization has to rotate, because if you remember in a hysteresis curve, you can have a polarization in this direction and then in this direction. So if I have a polarization along the triple one axis, then if I have to take it from this point of the hysteresis curve to this point of the hysteresis curve, it should move from 1 bar 1 triple one to triple bar 1. So that kind of polarization switching is essential. Okay, so now that means if I have polarization that are equal and opposite, I can say that the region that has triple one polarization and region that has triple one bar polarization is having a 180 degree domain wall. And now the angle between this polarization and this polarization is like 71 degree domain wall. You can have regions that has this polarization and this direction of polarization, and then you can also have polarization along the face of that. Okay, and that will be like 109 degree domain walls. Okay, so you can have all 3 possible configurations of domains in this particular system where you have triple one polar axis. So when I have 8 equivalent polar axes possible in a given system based on the crystallography, I can have 71 degree domains, I can have 109 degree domains, I can also have 180 degree domains, and which is present in bismuth ferrite. Okay, and now how do I measure these domains, or how do I kind of look at whether these domains are present in this material or not? One of the measurement techniques that we use is called as piezo-force microscopy. Here what do? We have a tip that is coming up with an electric AC signal attached to the sample as well as the tip. Okay, so now the tip is coming here and is going to experience the force that is coming from the electric polarization. Okay, so now when I have a polarization along in this axis and then my tip is coming here, my tip is going to experience components of polarization. In this direction, the tip is coming from vertical top and my polarization is in this angle. So I can have components of polarization experienced by the tip. So the tip can experience vertical and lateral forces. So that is how I can find out what are all the different domain patterns that I have. I can find out whether all my domains are upward and downward oriented, or all my domains are left or right oriented based on the piezo response force microscope. So the piezo response force microscope will facilitate me to figure out what are all the domains that are top and bottom, and what are all the domains that are left and right. Okay, so that is the advantage we have when you are using a piezo response force microscope to study the domains in the system. Okay, how does the domain pattern look? Okay, this is called as a fractal domain pattern. This is the topography, and this is the out of plane piezo response force microscopy. That means I have a polarization component and I am measuring the vertical force experienced by the tip. When I say in plane PFM or in plane piezo response force microscopy, that means I am measuring the lateral force experienced by the tip because of the polarization that is present. What does this color coding means? So the dark one corresponds to either upward or downward polarization, and the vice versa for the bright one. Okay, so that means the regions of dark can represent polarization that are components that are perpendicular to the sample surface, and the white ones can be the polarization that are downwards perpendicular to the sample surface. And the in-plane PFM, the bright and dark contrast tells me I can have a lateral orientation of left and right orientation, or vice versa. The bright one can be either left or right, and correspondingly the black one can be left or right or left. The opposite is what we can assign. So we can also measure the piezoelectric displacement as well as the polarization hysteresis curve from this equipment. So we are capable of measuring a ferroelectric domain, looking at a ferroelectric domain, and then looking at the piezo-response behavior of these systems in a in the ferroelectric state of a bismuth ferrite. Now comes the strain engineering. Okay, so now I have established such a behavior. Okay, so now I have established to use certain things. A bismuth ferrite can be grown epitaxially, and then it will have a cubic construction. And if it has a cubic construction, I can have a polarization along the 111 axis, and I can measure those domains based on the piezo response force microscopy. And if I use the piezo response force microscope tip, I will be able to measure individual components of polarization that is acting upwards as well as lateral, so out of plane as well as lateral, left, right, up or down. That will be based on the color contrast that we get. But now what is interesting is strain engineering. We can take a material, and in the bulk we know that high pressure studies are done. You take a material and then you apply some stress on it, and then that can give rise to a change in structure as well as the property of the system. And now the change in strain engineering can be achieved in thin films or nanostructures by this epitaxy principle. So if you remember, I said I will use a single crystalline oxide substrate. So now if you imagine this blue one as a substrate and these yellow ones as my film, so the blue lattice parameter will force the yellow lattice parameters to take the same lattice parameter of my substrate. That I call it as epitaxy, and that I call it as a strain growth of the system. Why? Because that is not its natural lattice parameter. Because the substrate is bulk in nature and the thin film that I am growing is very nano in dimension, the thin film is experiencing a strain from my substrate. So the lattice parameter of the substrate is kind of straining my lattice of my film, and that is what it happens. So now I am going to do a strain engineering on bismuth ferrite and see what happens. How do I apply strain? Strain can be applied by heterostructure. Sir, what is a heterostructure? I take two dissimilar materials, I put them together, I call it as a heterostructure. But now what I can do in PLD is I can actually create enormous amount of interfaces, which I call it as artificial superlattice structures. And when I create enormous amount of interface in these materials, there is a continuous strain transfer that is happening across. So what is the advantage of this? Why do I worry about this kind of a, what is the advantage of having this? Now if you remember, I said you can have a substrate and then you can have a film. Now if the film thickness is increasing, if the film thickness is greater than 20 nanometer or so, people know that the strain used to relax. So that means you will not capitalize on the strain that you have imported. Strain is relaxed. So now if your strain is relaxed, then you will not be able to grow a film that is beyond 30 nanometer or 40 nanometer. So now how do you carry forward the substrate strain across the thickness of your film? Your film can be even 400 nanometer thickness. Your device may expect a film thickness of 400 nanometer. Then if you want a substrate strain that is transferred across the thickness of your film, you will be in trouble. If you do a single layer deposition, you will not be able to transfer that strain. Okay, so our interest is to transfer the strain across the layer, across the thickness of the layers, and that is why we go for this option called as superlattice kind of a configuration. So basically, my individual layers will have very small thicknesses. If you see that superlattice is represented as like bismuth ferrite and strontium titanate, M and N. M represents the number of unit cells of bismuth ferrite and N represents the number of unit cells of strontium titanate. And that is how I have labeled in this presentation. This is a TM of what we have grown. Okay, so basically these are very well known things. Okay, we are not the inventor of this methodology itself. This is known in literature, where you can grow artificial superlattice structures between different layers that are present, different layers that you are dealing with. So what we are establishing here is you can have, let's say, four unit cells of bismuth ferrite. You can have few 8 or 10 unit cells of strontium titanate, and you can still maintain a very atomic coherency across the interface. That is what we established. Now, if you look at the diffraction pattern, you can obviously see there is something called as superlattice spots around every individual diffraction. So these satellite peaks are called as superlattice reflections, and since these reflections are coming from the nature of the growth along the c-axis only, I call this as artificial superlattice. You can have superlattices that are coming naturally in systems based on either aligned octahedral tilt or composition ordering. Conventionally, people know superalloys and superstructures are known for giving rise to superlattice reflection based on composition ordering. So here we create a compositional ordering with a larger translational periodicity only in the z-axis. And now, what is the achievement we have got? So now if you remember, I was talking about a PFM which is showing contrast out of plane and in plane. You look at this study, you can have any kind of reversal arrangement possible. If you look at this image, we get a very beautiful contrast in the out of plane, and we don't get any contrast in the in plane. Okay, so what is the meaning of this? Which means I had a polarization that is present, and my tip has come here to the sample, and it is experiencing upward force and downward force. And when I am asking it to experience a lateral force, my tip is seeing zero force there. That is what this means. When there is no contrast in the lateral force, that means there is no lateral component of polarization. Sir, how is it possible? If I have a 111 axis rhombohedral structure, that means my spontaneous polarization has to be along the 111 axis. And now I have the artificial superstructure. Now it looks like I have polarization only along 001 axis. And I don't have the component at all. So now I'm not experiencing the component of lateral periodicity at all. That means I am constraining my polarization along the c-axis only. So crystallographically, when is it possible? Crystallographically, it is possible only if this rhombohedral structure transforms into tetragonal. Because we all know tetragonal is the only structure that has 001 polarization as the axis. So now we verify that. No planar component is observed. Yes, we collaborate with theoreticians, and they have confirmed that yes, when you have a very constrained configuration that is coming in both the directions of bismuth, right? You can have polarization coming only along the c-axis. That means you get a kind of tetragonal structure. But we also do more experiments. So if you look at the reciprocal space mapping from the experiment of superlattice, you see that the substrate and the buffer layers as well as the superlattice structure, everything takes the same structure, and we end up with a same planar lattice constant but a different out of plane lattice constant. And that is nothing but your tetragonal structure. That means you have A is equal to B, but C is different. Such a scenario, we all know that comes from tetragonal structure. But that's not the story here. Okay, so based on strain, we have changed the crystal structure itself. So the collective evidences suggest you can have tunable strain condition enforced. And these tunable strain conditions can give rise to structural constraints in the unit cells. And now if a bismuth ferrite tetragonal phase could be achieved by artificial superlattices, can we achieve this strain under normal conditions? That's the next question we are going to ask. Do we always need a superlattice structure to have tetragonal phase of bismuth ferrite? Okay, that is what we are going to discuss now. Okay, but it is not true. The superlattice, if you remember, so this was like much early work of ours in 2010. Then after the superlattice, you could see that people could grow individual layers, basically take bismuth ferrite. Look at these numbers here. You take bismuth ferrite on strontium titanate, grow it to 2 micron, then you will get a rhombohedral structure. grow it to 270 nanometer, you will get a rhombohedral structure with a small monoclinic distortion. And you change the substrate, you take it to lanthanum aluminate, then you will get a grow it of, let's say, 20 or above nanometer thickness, you will get a tetragonal-like structure with a very weak monoclinic distortion. But now you substitute bismuth with barium and then grow it on lanthanum aluminate, you will end up in a tetragonal structure. So here are the details of the study. So this is in literature. This is not our work. Okay. So the graph also comes from the same paper that I am showing on the left side. So now the question comes. How do I know if I have different kinds of structures and what happens to my polarization when I move from one type of structure to another type of structure? So I can have a rhombohedral structure. A rhombohedral, I know I have established very well. You have a 111 axis and then you should have polarization components on all three different kind of domain walls possible. But when you have a monoclinic MC kind of structure, then the polarization component is along the face of the unit cell. And when you one of the face of the C axis, and when you have a MA kind of distortion, you have along the 110 axis. So basically, when you have a rhombohedral system, the polarization is pointing in this axis. From there, it is coming to this face, and then it is reaching to this face of the system, and it reaches to this edge of the cube. So you end up in a tetragonal kind of symmetry. The schematic shows here. In ferroelectrics, you can have rhombohedral, and then you can have a monoclinic kind of rhombohedral, then you can have a tetragonal kind of monoclinic distortion of tetragonal structure, and then you can have a completely tetragonal structure. What is this transformation between rhombohedral to tetragonal via monoclinic distortion? If you remember today's morning talk also, you would have experienced this word called morphotropic phase boundaries in ferroelectric systems. When you deal with morphotropic phase boundaries, you move from one type of crystal structure to another type of crystal structure when you change the composition. But now, looks like based on strain, I change the strain configuration and then I am moving from one crystal structure to another crystal structure. That is almost, I am creating a morphotropic phase boundary kind of scenario just by strain. Okay, how can I impart strain? Yes, in thin film community, most of people know that strain is imparted by substrate. So you can have variety of substrates based on the different materials that you deal with. So this is taken from a review article which you can find out everywhere. Okay. So now, if strain is the key parameter, I want you to remember how the earlier literature achieved different structures. So basically, you take strontium titanate, grow very thick film, you will get rhombohedral. You take strontium titanate 001, you grow thinner film, you will get monoclinically distorted rhombohedral. You take lanthanum aluminate substrate and then you grow bismuth ferrite, you will get a monoclinically distorted tetragonal. You take bismuth ferrite, substitute barium, and then you will get tetragonal. That is what has been established so far. So what we tried is, we take the lanthanum aluminate substrate, and we know that substrate strain is what is transferred to the film. Now we are trying to have an intermediate layer which can tune the strain condition. If you remember in earlier slides, I said I can have a substrate and then I can actually alter the strain condition based on thickness. So I have a substrate, a very thin film can be completely strained. It can be completely strained. Then if I increase the thickness, I can reduce the strain. The strain get relaxed. So we are using the same idea in the same substrate. So we are going to fix the substrate. Everywhere it is 001. We are not going to change the chemical composition of bismuth ferrite as well. So we are going to retain bismuth ferrite and we are going to retain the same substrate, but we are going to use an intermediate layer which is going to control my strain. Okay, that is what we are doing. So basically we are growing three different configuration of samples where there is something called lanthanum strontium manganate. We will come to that later in the question section. So I am growing 2 nanometer of LSMO, which is kind of completely strained. So the substrate strain is transferred to LSMO because the thickness is 2 nanometer, and this LSMO strain is governed on bismuth ferrite. Now the next one. This one is partially relaxed. Partially relaxed because of the same reason I said, if I increase the epitaxial thickness, the strain starts relaxing beyond certain thicknesses. But now I fix at 10 nanometer, so I create a partial relaxation. And then I go to 20 nanometer such that this is completely relaxed. Now what happens to bismuth ferrite when I do this kind of strain conditions? You see, LSMO 2 nanometer, complete bismuth ferrite tetragonal phase, partially relaxed, a mixture of tetragonal and rhombohedral. So you have some amount of rhombohedral, some amount of tetragonal. So you have a mixture phase here between rhombohedral and tetragonal. Completely strained relaxed. Tetragonal has disappeared and you have only rhombohedral BFO. BFO-R, BFO-T plus R and BFO-T. So by playing the strain condition, I can achieve specific crystal structures. Okay, this is a reciprocal space mapping where you have partially relaxed strain. Here the lattice parameter of the substrate, the intermediate layer and the bismuth ferrite tetragonal is in the same line. Just for convenience, the data is split into two, but as such it is the same HKL values. Okay, and now this is the partially relaxed. So the rhombohedral phase is slowly emerging, and then you see here the tetragonal phase completely disappeared and you get only rhombohedral phase. Okay, it's a completely relaxed kind of a situation. Okay, so these are all numbers. So we can calculate from in-plane lattice parameter, out-of-plane lattice parameters. We can calculate strain experienced on XY plane as well as the Z axis. Okay. Now what did we observe? When you have a tetragonal film, you see only out-of-plane polarization. The in-plane polarization is almost to 0. But when you have a mixed phase, you get not only out-of-plane polarization, you also start getting a mixture of in-plane polarization. Okay, the left side is out of plane and the right side is in plane polarization in the BFM. Okay, so now when you get a rhombohedral phase, you get back to the fractal domains that I was discussing earlier. So basically, by strain, I am able to tune the polarizations based on only out of plane, tetragonal MC kind of phase, a mixed phase, and then a rhombohedral phase. So we could see a clear transformation of domains with sharp boundaries to fractal type domains. And that is driven by the structure. Of course, we always collaborate with theoreticians, both through first principle as well as phase field modeling. And Dr. Shashwata of material science is our phase field model person. So who simulates the ferroelectric domains of this bismuth ferrite in tetragonal phase, mixed phase, as well as rhombohedral phase. And we see something very interesting. This is the experiments. This is the left one. I think I hope the pointer is visible. So this one is the out of plane polarization experiment and this is the in plane polarization experiment, and here you see the out of plane polarization of the theory, which has only 001 and 001 bar component present when the domains are simulated theoretically for the given strain configuration. So now you can also have a mixed phase where the other polarization components are showing up. You see, you have a partially tetragonal, so you have 001, 001 bar. So you can also see the green and the other colors coming, which is coming from the 111 axis. So after a while, when you completely transform the structure, you don't have any 001, 001 bar. You always have a mixed components of only 111 axis. So basically, with the strain, we are able to achieve a morphotropic like boundary. Sir, what is the use of it? Yeah, of course, everything has to have some application. Yeah. So now for a 20 nanometer bismuth ferrite, so far, if you have a single phase, you get around 10 to 12 picometers per volt as the piezoelectric coefficient. And if you have a single phase of rhombohedral, you get 14 to 16 picometers. But when you have a mixed phase, remember, you are able to create a morphotropic kind of phase boundary. The value has increased to 200% or more. Remember, it is still 20 nanometer of bismuth ferrite. At 20 nanometer of bismuth ferrite, if you grow it in pure rhombohedral structure, the piezoelectric coefficient is around 15 to 18 picometers per volt. But for the same 20 nanometers, if I grow it in the mixed phase, I am getting 40 to 44 picometers per volt, which is kind of more than double in the terms of increment. This is the interesting thing one can do with strain. Okay, so you can use strain and then you can use that strain to alter the crystal structure itself. Okay, and now I will slightly touch upon ME composites if time permits. Okay, I think in another 5-10 minutes I will brief up on what ME composites are done or what we have done in ME composites, and then I will go to the summary. I will not hold you beyond 4:30. Okay. Okay. So the strain in multifunctional nanocomposites is another topic based on the application perspective. You all know this. I have already discussed this. What is magnetoelectric effect? Okay. The problem is bismuth ferrite is the only material that is available at room temperature multiferroicity or magnetoelectric multiferroic. So, and on top of it, it is a type 1 multiferroic. So, coupling is weak. So, its magnetoelectric coupling is going to be weak. In addition to that, there is iron present, which also gives rise to a lot of unwanted leakage currents possible in bismuth ferrite. So, now people work on composites. To overcome this kind of single phase limitations, people work on composites. Okay, so when you have an Me composite, you can have, let's say, two different phases. Let's say you can have magnetostrictive phase, and then you can also have a piezoelectric phase. Okay, so when you have a magnetoelectric, you can have magnetoelectric effect, which is coupled through strain when you have a piezoelectric material and a magnetostrictive material put together. So here strain is kind of interrelation. So basically, if you remember that I have this pyramid, the Nye pyramid. If you remember, I had polarization and electric field, and the electric field interacts with strain. Then I call it as inverse piezoelectric effect. And then if the stress interacts with polarization, I call it as piezoelectric effect. And similarly, I can have magnetization and H. If magnetic field is introducing some strain in it, then I call it as a magnetostrictive material. When I apply some stress and then I induce a magnetic moment, I call it as magnetostrictive material, and this is called as the inverse magnetostrictive material. And the strain is kind of coupling all of this in this kind of composites. In the earlier section of the talk, I tried to focus only here, and then I tried to use this to alter these conditions. But now we are going to use this for the property itself. So this is going to decide whether you are going to have an Me coupling or not. Okay. Of course, there can be a lot of systems that can be chosen for the composite structures. I will not go into details. And we have chosen something called as a lead-free piezoelectric, which people call it as BCZT. And we have chosen it for the ferroelectric or the piezoelectric phase. And we have chosen cobalt ferrite for the magnetic phase. I will quickly touch upon the highlight of the study. Okay. So I will not go into the further details of it. And I will only say what we have tried to do here. Okay. Yeah. When we come to composites, you can have different phases in different connectivity. So basically, I'm going to talk about composites where one of the piezoelectric phase is BCZT and the other magnetostrictive phase is cobalt ferrite, which is an inverse spinel cubic structure. Okay. So you can have different connectivities. One is 0-3, the other is 2-2, and the other is 1-3 structure. These are the different connectivities possible. So what does it mean connectivity? One of the phase, if this is 0, the red one is a 0 phase, that means this particular phase 1, which can be any of them, is connected with the same phase is not connected in the same phase in any direction. That means it is connected with the other one in the 0 direction. That is called a 0 connectivity. Whereas this phase is connected in all 3 axes. So you start from this point, you reach there. You start from this point, you reach there, and then you start from this point, you reach there. In all 3 directions, the one of the phase is connected, but the other phase is not connected in any of the direction. Then I call it as 0-3 connectivity. And here it is 2-2 connectivity. So what does it mean? This orange phase is connected in both directions, but not in this direction. If I start from this point, in this direction there is no connectivity. But I can have connectivity in these 2 axes for every material from this end to that end. So I call it as 2-2 connectivity. And then so on. You can see it here. So this orange phase is connected in one axis, but not in the other 2 axes. However, the blue one is connected in all 3 axes. So these are the different connectivities possible in composite materials. Okay. But we are going to obviously talk about 2-2 because 0-3, you have to always have the insulating phase as the 3 connectivity because of the leakage current, the D0 non-D0 problem you should remember. Okay, if I have the magnetic material connected in all 3 directions, it will give rise to leakage current. Even if it is connected in one direction, it may give rise to leakage current. So we have to work with something called as 2-2 structures for thin films. There is enough literature. Okay, I will not go into the literature. So we have chosen BCZT and CFO, and we have chosen superlattice kind of behavior or multi-layers of CFO and BCZT, but except with we have done one modification here, we have not gone to an epitaxy. But we are trying to connect all columnar grains, and every grain is connected with an atomic interface. See, if you go epitaxy is a costly affair. You need to have high costly single crystalline substrates, and then you will also end up in a lot of anisotropy. If you remember the previous presentation, there is a huge anisotropy involved. There is no polarization in the planar axis. There is only polarization in the upward axis. Such an anisotropy will give rise to a device anisotropy also. But so, polycrystalline materials are preferred to minimize the anisotropy, where these properties are crystallographically decided and they inherently have anisotropy property. On top of it, if you have only epitaxy, then you will have double anisotropy involved. Okay, so that is why we decided to go with polycrystalline materials, and only thing is we want to get kind of simulate this nanorod kind of structure based on morphology and then achieve the connectivity. Again, we do pulse laser ablation, and what did we do? We tried to optimize individual layers, and we know from the experience as well as from the literature, if you provide the right condition, you will be able to grow layers as vertical columns. You can grow grains of different orientation as vertical columns. So that is what we are trying to do now. We try to grow vertical columns, but at the same time, the interface between one layer and the other layer, we want to retain it like an epitaxy. Okay, so we capitalize the interface, which is very essential for this composite to transfer strain. A strain is transferred only when you have a sharp interface. Otherwise, the strain will not be transferred from one phase to another phase. That is very well known. So to capitalize the sharp atomic interface and to capitalize this kind of anisotropy problem and to address the anisotropy problem, so we try to grow a polycrystalline material but with a columnar grain structure. So between these, in a single column, the interface between one phase and the other phase is very sharp. Of course, we have to study the interface. So you can clearly see that the interface between, this is the bottom interface and this is the top interface because it's a sandwich. So you can clearly see that the interface is very sharp. So there is not much of an undesired phase at the interface. You can also see the lattice parameter FFT pattern of BCZT here and CFO here. You can also see an FFT pattern taken exactly from the interface. That means you have a very coherent Fourier transform pattern. That means you have a very lattice matched growth across a single column. This line is representing a single column in the left side graph. This is BCZT and this is CFO. Look at the lattice parameters, which is 0.25 nanometer, and here also it is 0.252 nanometers. And that means this is the grain boundary between one column and the other column. So we are able to achieve an epitaxy-like condition. Look at these lattice parameters here. This grain of BCZT is 0.25 and this grain is 0.25. So we are able to achieve an epitaxy kind of a condition. And now that is not observed in one column. We have observed it in various columns. Sir, how are we able to achieve this lattice matching? You look at this. The 111 HKL is 0.23. But the HKL of CFO 311 is again 0.25. And if it is 200, it's 0.201 and it is 0.209 or 400. So basically, the unit cell of cobalt ferrite is almost twice the time of BCZT. So we are able to capitalize the crystallographic orientation of the lower order from BCZT and the higher order from CFO. And that is how we are able to achieve this kind of and what did you achieve? Basically, what you achieve from this, you look at the magnetodielectric behavior percentage. So maximum reported so far for similar structure is 13%, and we see around 21 to 24% of magnetodielectric behavior. Okay, so now I will not go into much more details. So basically, the fundamental question what somebody will ask is, how do we get the maximum response out of these composites? So people have done calculations in bulk, and they have told that when you have a 50-50 volume fraction of both the phase, you will get a maximum response from the ME composites. But here it is done in bulk, and the above equation has no consideration of strain that is involved at the interface. Okay, that is something I want to remind everybody. So what we do here is we try to capitalize on the strain that is present at the interface. Sir, how do we capitalize the strain at the interface? The first question is, we should know what is the volume fraction that is giving the maximum property as per the simulation. Okay, so we changed the volume fraction as the thickness ratios are changed. And what do we get? The piezoelectric behavior. Yes, this is the piezoelectric behavior, and this is the inverse magnetic behavior, because we calculate the piezo coefficient in the presence of magnetic field. And you look at the response, the 50-50 composition as expected by the theory gives the maximum change in D33 with respect to the constant magnetic field. Okay, so now that is established now. So if that is the case, any system which has a 50-50 volume composition should give superior property, but which may not be true, because there is a role of strain to play there. Okay, how do we establish that? We grew another same 50-50 composition, but without a coherent interface. The volume percentage is 50-50, but the interface is collapsed. So there is no strain transfer between one layer and the other layer. Then you see the magnetoelectric coefficient is almost 0. Only on the layers where we have sharp interface and where the strain is effectively transferred, we are able to get a superior magnetoelectric coefficient, almost 800 millivolts per centimeter Oersted. Is a very large number for these composites, especially for thin film composites, which are of 400 to 500 nanometer thickness. Okay, so now our interest is, I think in another 5 minutes I will stop. Okay, so our interest is how to estimate the strain and how to use what is the optimum size for the strain. Okay, of course we use a GA-XRD. If anybody is interested, I will explain it in much more detail later. So when we keep on increasing the glancing angle of the XRD until 0.5, I don't see CFO peak at all, because CFO is buried under BCZT. So now when it is buried under BCZT, if I keep my diffractometer of the grazing incidence at 0.5 to 0.55, that means my X-ray is looking at the interface. So my diffraction pattern is coming from the interface of the material. That is what it means. So what we did, we tried to calculate the FWHM of the layer as a function of grazing incidence. If you have an individual BCZT layer of the same thickness, your FWHM continuously drops as your grazing incidence is increasing, because this is very conventionally known in X-ray diffraction. The moment you increase your grazing incidence angle, your volume penetration depth of XRD keeps increasing, and then the FWHM keeps shrinking. So here we have the same microstructure and the same grain size, which we have estimated from the other techniques like SCM as well as the other techniques. And now we are trying to do the same experiment on the composite BCZT orientation and the individual BCZT orientation. So now if you see the FWHM of the composite, there is a spike at 0.55 and then it comes down. So you all know that strain can be calculated from a simple X-ray diffraction. Peak width, the FWHM of the X-ray peak width can be used to calculate the strain that is present in the particular grain. Okay, so we are able to capture the interfacial strain around this particular angle. If you remember in the previous slide, at 0.55, I am dominant, the X-ray is looking at the interface. Between 0.5 to 0.65, my X-ray is looking at the interface diffraction pattern. So that is how I am able to estimate the strain. And then if you look at the strain that is involved, that is close to 7% of strain. Okay, now we are making a hypothesis. So based on this alpha, we calculate some penetration depth, and then based on that penetration depth, we are going to decide what should be the thickness of individual layers. Yeah, because if I have a thickness of 500 nanometer and 500 nanometer, and if the strain is not realized by the other layer at all, then we should know what is the optimal range the strain operates. And our hypothesis based on this experiment is strain operates up to 40 nanometers on either side of the interface. So now we try the same thing to create superlattice structures of 40 nanometer periodicity. So there is a strain transfer effectively happening across the thickness. Sorry for the poor quality of SCM. This is the best we could get because of the charging effects in these multi-layers. Okay, so fine. So what we see is we change the periodicity and then we try to do the magnetoelectric behavior and the inverse piezomagnetic behavior. You look at the percentage increase here. When I have a 40 nanometer periodicity, I get around 25% of variation in the inverse piezomagnetic effect. So now that is what is observed as an effective strain transfer dimension. If I increase the thickness, see all of them on the left side are all 50-50 composition. because the volume fraction of BCZT and CFO is the same. If I use the same bulk expression, which tells me the average property is always high at 50-50, then all of these samples should have a superior property. But now the strain has a unique role to play in effective transfer of the property. That is why I am getting a superior property at 40 nanometers. This is another example of the study. For 20 nanometer and 40 nanometer, you can see such a linear piezoelectric effect. So once the strain relaxes, you see that the sample is transferring from linear response to non-linear response. Basically, piezoelectric to electrostrictive characteristic is showing up. Okay, so I think I will quickly stop here and wind up the conclusions of the study. Okay, so in this composite, we were able to identify the operational range of strain, especially in polycrystalline BCZT with a coherent interface. Okay, and we could also estimate what is the strain operational range even in polycrystalline columnar growth systems, not epitaxy. It is one to be remembered. Okay, so we have also achieved a grain-to-grain epitaxy-like interface, because there is a crystallographic relation between one layer and one grain and the other grain of the layer. Okay, and we could also see an extended linear response of piezo response even up to 10 volts. Okay, I'm talking about a 400 nanometer film, so I'm applying some 10 volts, I'm applying some 0.25 megavolts per centimeter kind of a number. Okay, so such a large electric field it is able to withstand, and it is giving a linear piezoelectric response. So I'll quickly summarize. So I have introduced you about ferroics, brief about ferroics, and then I have also introduced you about what is multiferroics, because they simultaneously possess more than one order parameter. And then I have talked to you about what is magnetoelectric multiferroics, because having two order parameter is one, and having them interacting with each other is another ball game. So that is where I introduced you about magnetoelectric multiferroics, and then I introduced you a brief about types of multiferroics, and then I talked to you a little bit about PFM and its property measurement, and I have told you how strain can tune the structure of PFO both in the superlative structure and in the individual epitaxial structure for a given thickness. Okay, and I also told you about what is the effective strain transfer dimension when you have a nanocomposite, and especially when you are able to achieve a coherently grown nanocomposite, where one grain is crystallographically related to another grain, you will be able to quantify the strain across the interface. And interestingly, the strain operating range is also close to the electrostatic and the electromagnetic interaction operating range. That is another interesting thing which I have not highlighted. Okay. And just because I have gone through, there are a variety of people, a brief introduction about our group, what we do here at IIT Hyderabad. We are identified as multifunctional materials and devices group. And we also work extensively on ferroelectric polymers, as well as magnetoelectric nanocomposites. So we work on flexible polymers as well as for flexible devices. And the other things we do, we work on gas sensors, we work on compositionally graded actuators and sensors. We also work on flexible nanocomposites and phase change memory materials for different applications. Okay. And this is what our group generally work on. So we work on ferroelectrics, piezoelectrics, multiferroics based for sensor and energy materials, sometimes for polymer bio applications as well. These are all what we do. We try to understand the processing, the structure, and the force fields that are giving rise to the property, and then the functionality, and from there we develop prototypes. So that is what is the major activity of our group. And acknowledgement, of course, Dr. Kiran, ex-colleague and a good friend of mine, who has given me this opportunity to present this work here. And I hope in the last minute I had to rush a little bit, but I hope it is okay. So my students who have contributed for all this work that I am presenting, and then the funding agencies, DST as well as IIT Hyderabad and DAE, collaborators within IITH and outside IITH, and collaborators within the country, and of course family. Because my family is patiently waiting now, when will I finish this talk? Okay, so family is also acknowledged with due respect. So thank you, and I am ready to take some questions. I have exceeded by 7-8 minutes. Sorry for that.
Thank you for a nice talk. So I think we may have some interesting. So I request all the who want to ask the question, please raise their hands so that we can allow them to ask the question.
I see two questions from one Mr. Pravat Kumar Swine.
Yeah, I saw.
So the first question from him is: does the strain engineering affect your bismuth ferrite structure during the growth period? Okay. Yeah. So this is a very interesting question. What he's asking is, I assume that is what he's asking. So during the growth of bismuth ferrite itself, is the strain affecting the crystal structure? Okay. That is very difficult to answer because the growth is happening at a very high temperature. The growth is actually happening at 700, say 675 degrees Celsius. Okay, so we do not know what is the strain condition because we do not know what is the thermal expansion behavior of the substrate as well as the material. So basically the strain is imported only when the system is relaxed back or cooled back to the room temperature. So that is where is the net strain is involved in crystallizing. So basically when we cool the thin film, the crystallization process happens mainly in the process of cooling, because at 700 degrees Celsius, if I quench my sample, I will not get a proper crystalline material anyway. So the crystallization process happens mainly in the process of cooling. So what his question is, during the growth? No, we believe that the growth itself, the condensation, if you call it as growth, the condensation of the vapor phase on the substrate, if you call it as growth, definitely not. It happens actually in the cooling phase. That is one question. And he himself has asked another question. As you mentioned, LSMO 2 nanometer to 20 nanometer in the ideal range to relax the bismuth ferrite. Can it varies for such a study? I am not understanding what it is. See, this dimension is very system dependent. For bismuth ferrite, yes, 2 nanometer to 20 nanometer is the ideal range. But if I deal with a different structure, which is much more very close lattice match with LSMO, then probably the strain transfer can happen for much more thicknesses. So here, the strain transfer is still, to some extent, we should a priori know what are we dealing with. So the strain transfer range for 2 nanometer to 20 nanometer, if you are talking about an individual layer, yes, an individual layer grown epitaxially on a single crystalline substrate, yes, the strain will relax from 2 nanometer to 20 nanometer. It is known that above 20 nanometer, the surface is known to relax the strain. Okay, but when we are talking about heterostructure, then it depends on what is grown on top of it. That will decide whether the strain is completely relaxed or partially relaxed. So for bismuth ferrite with LSMO, we have observed this dimension, yes, but that will depend basically on the percentage of lattice mismatch that you are dealing with. You cannot take some other system which is having a very large lattice mismatch and expect it to be completely strained. Even at 5 nanometer, the system may relax because the lattice strain is much more larger. So basically, we should calculate the strain percentage, which is close to 5%. Without relaxation, you should have a 5% of lattice mismatch so that you can continuously import the strain from one layer to another layer. I assumed certain things and I have answered it. I hope he is happy.
Yeah, I agree with you. I think he want to ask the same thing for different.
Okay.
Kiran sir.
Yeah, Yes, Abhinav sir.
There is some echo in your voice, I think.
I don't know why.
I am not getting any echo.
Please continue.
So Abhinav sir, can I ask? Now it's okay, I think.
Yeah, it's all right. Please continue.
Yeah, Ranjit, there is one question. Which coupling is relatively higher among polarizability, magnetization, and elasticity? I think he is talking about magnetization, polarization, and ferroelasticity. Out of which one is relatively easy to measure?
Relatively easy to measure is the strain coupling. Because polarization and magnetization coupling is anyway inherently there has to be a ferroelastic strain that is coupling them, but measuring that will be basically, if I understand his question correct, he is talking about the MH stress strain interaction PE stress strain interaction and then PA-MH interaction. The PA-MH interaction is known to be weaker. The strain involved is known to give a weaker effect already, that we know that. So that is why we are going for the composite, where the strain mediated effect can be dominantly observed. Because of that reason, we are going for a composite.
But Ranjit, in general, for example, in polycrystalline, is it easy to measure this one ferroelasticity, because the signal may be very, very big?
No, ferroelasticity, I agree. But if you work on this intercoupling properties, individually, if you want to apply stress and strain curve and measure, it will probably be different. But if you want to measure inverse piezomagnetic effect or magnetostrictive effects, then it is possible.
Oh, okay, thank you, sir. Sir, there is one more question. How can we measure saturation magnetization? I think, yeah.
Yes, you need your MH curve. It's a textbook procedure. You take your MH curve and then go to the saturation point and draw a tangent to the curvature, and wherever it hits your y-axis is saturation magnetization.
Ranjit, may I ask 2 more questions?
Yeah, please go ahead.
There are some questions in the Google form. Can you please explain vertical and lateral force in contrast to the PFM again? I think you mentioned it, but someone want to have.
Is my screen still shared?
Yeah, it is shared.
Okay, fine. So in that case, I think I will go to that slide and then I will. Okay, so. Okay.
One participant also want to have the explanation about the super lattice reflection. So as you are going back in your presentation, you can cover both. Okay.
So especially, I think here I have, there is too much of, I will use this slide. This is much easier. So now this is my polarization axis. So this is my polarization axis. If I consider this unit cell, my polarization is acting in this axis. So basically what I'm trying to say is, when we have a cubic kind of a unit cell, I'll call it pseudo-cubic, and then the polarization is running along the body diagonal. Now the electrostatic polarization, we all know it is a vector quantity. I can call it as P1, P2 plus P3 based on IJKL. Okay, so that means I have a polarization along the body diagonal, which means I can have components in this direction, or the projection of this polarization in this plane and the projection of this polarization in the Y plane. So basically, when I bring a tip that is coming with an electric field, and assuming because it's a point sharp, so my electric field is coming in this direction, or the electrostatic interaction is coming in this tip axis, I have a polarization that is in this angle to this particular tip. So what will the force experienced by the tip? Actually, the force experienced by the tip is projection of this polarization in this axis, that will be called as vertical force. And then if I am asking the tip to experience the lateral force, that means the tip, when it is experiencing a vertical force, the tip will bend either upwards or downwards. And then I can also have, this is a small cantilever. The tip is actually a cantilever. So it can also experience the force in this axis. So it will give rise to a left or right deflection of the cantilever. That will be experienced because there is a polarization component that is acting on the plane also. So the components can be in this axis or in this axis, and the components can be in this axis or in this axis. So this is my 1111 polarization, and this is the component in the left-right direction, and this is the component in the plus Z minus Z direction. That is what I call it as, I bring the tip and then I measure the outward force or the force experienced by the tip because of polarization that is pointing upwards and the polarization that is pointing downwards. When I say polarization pointing upwards and downwards, I actually mean the components of polarization. Okay, I am actually talking about the components of polarization. Yeah. So when I'm talking about right, I'm talking about the concept of polarization in the planar axis. So that is what I'm talking about. Okay. Now going back to the lattice question. Superposition. So if you remember here, we know this. If I take a unit cell, we all know what is the D periodicity in every different axis. So we all know what are the unit cell parameters. Okay. And every diffraction pattern or any translation vector of crystal symmetry, you will know what is n1 of A vector, n2 of B vector plus n3 of C vector. So this is a translation vector that we define translation symmetry in crystal. Okay, what does it mean? I take a unit cell of bismuth ferrite. Let's take this point. Okay, this equation tells me n1 times in A direction, I will reach to the same surroundings. n2 times in B direction, I will reach to the same surrounding. And n3 times in C direction, I will reach to the same surrounding. And this n1, n2, n3 and ABC are all of unit cell dimensions. Okay, but here what happens, you see. I start from this point. N1, N2 is fine because I'm moving it in this plane and in the X and Y plane. The question comes when I move in the Z plane. Now N3 times of C. If I take the translation symmetry, 1 times of C, I will go from one unit cell to another unit cell. 2 times of C, I will go to another unit cell. 3 times of C, 4 times of C, I will reach the interface. Because BFO I have 4 unit cells, STO I have 8 unit cells. If you remember, I said BFO 4, STO 8. So now, after 8, you see this point and this point is the same point. Independently, I have n3 times of C vector. But after this translation, from this point to this point, the surrounding is the same. So, on top of the crystallographic periodicity, I have an additional periodicity, which is a summation of bismuth ferrite thickness plus STO thickness. So, that becomes an additional translation symmetry. On top of the atomic translation symmetry, there is an additional translation symmetry along this axis. It is basically having a diffraction grating. You have a diffraction grating and then you send a wave. What will you get? You will get a sin x by x curve. Exactly, that is what you get here. So basically there is an additional translational periodicity in the z-axis, and that will be decided by the difference between the first order and the 0th order peak. The periodicity can be calculated between the distance between this peak and that peak. That is what you do in your diffraction grating experiment in your basic physics course. You calculate the difference between this pattern to that pattern. That will give you what is the grating element width when you do a simple diffraction grating experiment. So that is what is seen here as a super reflection. The super reflection in this particular case is seen only along the 001 normal axis because there is a translational periodicity on top of the atomic periodicity imposed on it based on the growth condition. That is why I call it as artificial superlattice structure. And that is why I get a super reflection around the atomic periodicity. This cannot be away from the atomic periodicity because the Bragg reflection is taking care of the actual diffraction pattern. That is taken care by n3 times of C. What is D001? That is taken care by the unit cell. On top of it, I am superimposing an additional symmetry that is comparable, 12 unit cells. So basically, I am talking about 12 unit cells of 4 angstroms means 48 angstroms. I am talking about a periodicity of, let's say, 45 to 48 angstroms is what I am talking about here. So your C-axis periodicity is 5 angstroms in your unit cell, but in this periodicity is about 45 angstroms. So it is still comparable. You can still get a diffraction pattern around the D spacing that is present for the C-axis. I hope I have answered. I hope it is clear for the person. Anyway, I don't know if yeah.
I think so. So you explained very nicely again. So is there any questions? Because at my end, I do not have any more question. So, Dr. Abhinav, do you want to ask some question, or should we close the session? Okay, so if there is no more questions, I would like to thank our speaker, Dr. Ranjit, for a wonderful talk. It is very informative. You started from the basic, from the point charts, and let us to the devices, and you have explained us how you can engineer the structure by using the strain. So very nice talk, sir. Thank you very much for your valuable time.
Thanks a lot, Dr. Kiran, and thanks a lot for
Hope,
the answers.
hope to see you in person sometime when the things will get
Sure.
normal. So I would
Yes.
like to invite you here in the Department of Physics. And thank you very much. And it is a very nice talk. Everyone appreciate this. Thanks a lot.
Thank you.
Very much.
Thanks a lot. Thanks a lot, everybody. Bye. Have a nice and safe stay.
Thank you. Thank you very much. Jai Hind.
Thank you.
There's an announcement to the participants. So those who has not filled the feedback form, kindly fill the feedback form. Or if anyone has any query, feel free to send me the email. I will definitely reply whatever the query you have. Or if you have any question related to the if you want to ask any question from our expert, you can directly mail to them, or you can mail to me and I will pass your question to them. Thank you very much. Yes.
Good evening. Good evening, sir.
Yes, please.
Good evening, sir.
Yes, please. Yeah.
Sir, where I can get the feedback form, sir?
Okay. So
Because
okay, we have
session.
wait. We have posted the feedback form at the YouTube and as well as on the WhatsApp group. So those who are not on the WhatsApp group or YouTube, so you can send. I will send you the email, and you fill that form in next 1 hour or 2 hours. I will give you the enough time to fill that form. Okay.
In the morning section also we didn't get the feedback form.
Okay. Because we are facing some technical problem, and hopefully we will resolve it by tomorrow. Because I think you cannot chat, so that's why. So
Yes.
don't worry about the feedback form. We will also ask the general feedback form at the end of the session.
Okay.
So I will send you the feedback form now, and you can send the feedback for both the talk in the same Google form. Okay, I can do that.
Okay.
Any other things, please? Because you are allowed to ask the question, and they are very good expert. So please feel free to ask the question.
Okay, sir. Thank you.
Okay, thank you very much. Have a great time ahead. So now I will leave the meeting and I will send you the feedback form. Thank you. See you tomorrow at 10. I request you, please join by 10:15. When the so most of the people try to join at the same time, 10:30. So I request all of you again, please join at least up to 10:20.
Okay, sir.
Okay, thank you very much.
Thank you.
Sir, please send me feedback, sir.